Welcome to the Introduction to Programming with C# course. In this course, you will gain skills to think logically and solve problems effectively through programming. We'll guide you through developing algorithms, using data structures, and implementing control structures and loops to create dynamic programs. You'll also learn to build reusable code with functions and methods, mastering core concepts like variables, data types, and more. By the end of this course, you'll be well equipped to tackle real-world coding challenges and advance your programming journey. We will begin by exploring the foundations of .NET development and examine how Visual Studio Code integrates into your workflow. We'll walk through setting up your development environment, organizing project files, and understanding the structure of a .NET project. Then, we'll build on this foundation by applying core programming concepts, from variables and data types to debugging techniques. You'll practice writing simple programs in C# and create a small project consolidating your learning. Next, we'll explore object-oriented programming in C#, learning how to define and implement objects, classes, inheritance, and polymorphism. We will also cover common design patterns to strengthen your coding skills. Then, we will examine asynchronous programming, covering essential concepts like async and await, and learn how to build modern, responsive applications that handle tasks efficiently in the background. Finally, you will learn how to leverage Microsoft Copilot to enhance coding and debugging in C#, discovering how this tool can improve code quality, streamline your workflow, and easily tackle complex coding challenges. By the end of this course, you'll be ready to tackle real-world coding challenges with confidence and efficiency. We look forward to guiding you on this essential step in your programming journey.
My name is Paul Party, and I'm your instructor for this course. I've been programming computers since I was in my teens. I love programming because it's like solving puzzles while designing and creating something amazing. My graduate degree is in philosophy, where I learned how to become a better thinker. When I program computers, I can apply many of the logic skills I learned in philosophy. Computer programming not only enables you to build cool software, but I believe it can help make you a better thinker. I started my software development career at Microsoft when the internet was just getting started, and I participated in the internet revolution firsthand. I managed software engineering teams that worked on desktop and web-based software. The internet gave software developers, particularly those working on user interface, incredible new opportunities. From mobile interfaces to websites, software developers are not only creating software that's functional, but also works of art. In my career, I managed and worked with teams at both Microsoft and PayPal that focused on customer-facing interfaces and learned how to make them great. I also spent part of my 20 years at Microsoft in training organizations where I learned how to communicate challenging ideas to new learners. I also was fortunate enough to have spent 15 years teaching non-majors philosophy at a university in Seattle. This reinforced my ability to teach learners difficult concepts using ideas they can relate to. There's nothing more satisfying than to witness a learner having an aha moment where they understand something new. I'm really excited about this program. I believe Microsoft has some of the most powerful and exciting software development tools available, and I can't wait for you to learn about them. I'm confident you'll have many of the aha moments as you gain new skills and reinforce existing ones. The learning experience in this course is designed to give you a comprehensive understanding of key concepts through various learning methods. You'll be guided through interactive, engaging materials that help you build practical and theoretical knowledge. Whether you're interested in front-end, back-end, or full-stack development, this program has the tools to support your growth every step of the way. Throughout the course, you'll be introduced to core concepts and key ideas in videos. These videos are designed to help you understand definitions, processes, and essential steps clearly and concisely. You'll get to absorb foundational knowledge, setting the stage for deeper exploration as you move forward. And when you need step-by-step guidance, screencasts will provide you with a detailed practical view. These screencasts will show you exactly what's on the screen and how to work through specific coding tasks. The course also includes readings that reinforce the key ideas presented in the videos. These readings are more than just supplementary material. They're job aids. You can print them out and use them as a reference while working on assignments or activities, helping to apply what you've learned in real-world situations more easily. Small activities are included to help you check your understanding of key ideas. These activities provide quick, interactive opportunities to practice what you've just learned. After completing each activity, you can compare your work with a fully explained example and answer key. This ensures that you always know if your answer is correct. Practical experience doing tasks you would in a job within this field is essential, and that's where guided labs come in. These labs take you through the implementation of different concepts step by step. As you work, you'll receive feedback and helpful hints, ensuring you can get the help you need when you need it. It's the perfect opportunity to practice in a controlled environment while learning by doing. After completing the guided labs, you'll move on to independent projects, or you try it. This is where you'll put your skills to the test, applying what you've learned in the labs. You'll work through real-world problems, cementing your understanding of the course material. The course will culminate in a practical project leveraging Microsoft Copilot that you can use as a portfolio artifact when you begin your job search in this field. As you progress through the program, the portfolio pieces will become stronger and better representations of the authentic experience you've gained. They'll showcase your understanding of code and the ability to implement different concepts from the developer program. This course guides you step by step from understanding concepts through videos and readings to apply them in activities, screencasts, and labs. Each part of the course builds on the last, helping you gain knowledge and authentic experience. By the end, you'll have completed real projects that not only showcase your skills, but can also be included in your portfolio as you start your career. Everything you do here will prepare you for success as a developer. Let's get started.
Throughout this course, you'll complete several guided labs. These labs are meant to give you an opportunity to practice your newly learned skills in an environment where you can get help and feedback as you complete coding challenges. This video will describe how to complete the guided labs in this course. We will explore a guided lab together so that you'll know what to expect when you come to one later in the course. First, let's check the content leading up to a guided lab. This structured content ensures that you have exactly the skills you need to complete the task. In this instance, there is a practical application video that describes in detail how this concept is used in real-world situations. Following this practical application video, you can review a reading that explains the concept in detail so you can go through this content at your own pace. Next, you'll find a video that works through the guided lab itself. This video won't give you all the answers to the guided lab, but it will provide an overview of the upcoming questions and challenges. Lastly, we come to the guided lab itself. The guided lab is a simulated code environment where you can experiment with code and receive hints and feedback in a realistic coding situation. To start, I'll click Start. In this lab, step 1 is an introduction to if-else statements, so I'll click Begin. Below the simulated code environment, I can find the specific instructions for this lab. Declare the variable age as type int. Place your cursor into line 2, type your answer, and select Enter to check your work. Alright, I think I know this one. I'm going to type in INT and hit Enter. Great, I got that correct, and I got a bit of feedback about my correct answer. To move on, I click Continue. And these instructions say, prompt the user to enter their age, place your cursor into line 4, type your answer, and select Enter to check your work. This one is a little trickier. Let me try type your age. Got it. This feedback for my wrong answer points me in the right direction. Let's try that again. I'm going to erase what I had here and then enter your age. Perfect. I'll click Continue. Let's try one more. Convert the input to an integer using int.parse and store it in the age variable. Place your cursor into line 6, type your answer, and select Enter to check your work. I'm not totally sure here, so I'm going to click on Hint and get some help. And the hint says use console.readline and then an open and close parentheses, display a message asking their user for their age. Great, that helps. I'm going to click continue and type in console.readline. And I've got it. That's how you work through a guided lab. Some questions will require more complex code to complete, so make sure you're using the hint function when you need it and reviewing the feedback provided for your right and wrong answers. Have fun completing these coding challenges that put your new skills to work.
In today's rapidly evolving tech landscape, artificial intelligence plays a key role in making development more efficient and intelligent. That's where Microsoft Copilot comes in. Microsoft Copilot is a powerful AI-driven tool that can assist developers in writing, optimizing, and debugging code. In this course, you'll leverage Copilot as a thought partner and a code-generating assistant, helping you solve problems, generate code snippets, and enhance your projects. The goal is to provide you with hands-on experience using a tool that real-world developers use to improve their workflow. In the last module of this course, you'll engage in videos, screencasts, guided labs, and independent projects that integrate Copilot. These labs will take you through how to use specific prompts to generate code, optimize solutions, and solve problems. You'll be shown step-by-step how to leverage Copilot's capabilities to strategically approach the final project. During the guided labs, you'll get hands-on experience working with Copilot. These labs are structured to show you how to craft effective prompts and work with Copilot's code generation features. You'll use it to assist in writing code, refining your solutions, and debugging. This practice will prepare you for the independent work you'll do in the final project. After the videos, screencasts, or guided labs, you'll move on to independent activities where you'll take control. Here you'll use Copilot to assist with various aspects of the project. You'll be making strategic decisions, but Copilot will support you by generating code, suggesting optimizations, and helping you troubleshoot. This prepares you to work more independently while still having the power of AI to assist. The final project will combine everything you've learned in the course, and you'll have Copilot as a key tool in your development toolkit. You'll use Copilot to help you generate and refine code as you combine the concepts from earlier lessons. The project is a portfolio-ready artifact showcasing your coding skills and your ability to leverage AI in modern development workflows. To succeed in the final module, actively engage with the guided labs and practice using Microsoft Copilot effectively. The videos and prompts will take you through Copilot and equip you to apply it strategically and independently. By the end of the course, you'll be fully prepared to complete the final project and demonstrate your skills using traditional coding and AI-assisted workflows. Welcome to the course. In this video, we will discuss how you can make the most of each part of the course to set yourself up for success. Whether you watch the videos, complete activities, or work through hands-on labs, each element has been designed to help you master the skills you need to become a confident and capable developer. The first step in every lesson is the videos. You'll be introduced to new concepts, definitions, and key ideas. Watch these carefully and take notes on the important points. The videos provide the foundational knowledge you'll need to build on, so don't skip them. They'll give you the context to understand everything that comes next. After each video, complete the readings. These readings reinforce the key ideas you've just learned and can serve as job aids. I recommend printing out the readings or saving them for quick reference. They'll be extremely helpful when completing activities, working on projects, or just needing a refresher. They're not just supplementary. They help you apply what you've learned to real-world tasks. Throughout the course, you'll find small but impactful activities. These quick exercises allow you to check your understanding of key ideas. Don't rush through them. Take the time to work through these activities thoughtfully. After each, compare answers with the answer key to check how well you understand the material. This is your chance to practice without pressure. At the end of each lesson, you'll encounter practice quizzes. These quizzes are a great way to ensure you fully grasp the concepts from the videos and the readings. Use these as a checkpoint to assess how well you retain the information. If you find yourself struggling, review the videos and readings again. The goal is to build confidence and solidify your understanding before moving forward. When you need to see the material in action, screencasts guide you. These videos show you exactly how to work through certain tasks step by step. If you ever feel stuck or unsure about applying a concept, watch the screencasts and follow along. This hands-on guidance is invaluable for understanding how the code works in real time and applying what you've learned. At the end of each module, there will be graded quizzes. These are an important part of your success as they allow you to demonstrate mastery of the material. These quizzes build on the practice quizzes, and they're a great way to ensure you're ready to move on to more advanced concepts. Treat these quizzes as milestones. Passing them means you're fully prepared for the next challenge. The guided labs are where you'll take the concepts from the lessons and apply them in a controlled, hands-on environment. These labs will take you step by step through tasks, including helpful feedback and hints. The more effort you put into the labs, the more you'll get out of them. It's all about learning by doing, so take your time and ensure you understand each step before moving on. After you've completed the guided labs, it's time to test your skills with independent projects or U-try-its. This is where you'll apply everything you've learned without step-by-step instructions. These projects are a great way to gauge how far you've come and to put your knowledge to the test. Don't worry if you feel challenged, that's part of the learning process. By completing these projects, you'll reinforce your skills and build confidence. Finally, at the end of the course, you'll complete a culminating hands-on project that you can use as a portfolio artifact. This project will showcase the skills you've gained throughout the course and give you something tangible to present to potential employers. As you progress through the program, these portfolio pieces will become stronger representations of your hands-on experience and understanding of key concepts. Success in this course comes down to using all the tools available. Watch the videos carefully, engage with the readings, complete the activities and quizzes thoughtfully, and take full advantage of the screencasts, labs, and projects. Each element of this course is designed to help you master the material step by step. By the end, you'll have a solid understanding of the concepts and real projects to prove your skills. Remember to persist, take your time, and you'll be ready for a successful career in development. Developing a functional library management system takes careful planning and step-by-step execution. With Microsoft Copilot's assistance, you'll work on a project to build, debug, and optimize a system that allows users to manage a library of books. In this video, we will explain the end of course project. This project simulates real-world software development. You'll start by building the basic features of a library management system, then debug and refine your code as it becomes more complex. By the end, you'll integrate everything into a fully functional and optimized product. The goal is to experience the complete coding process, writing, debugging, and improving your code. First, we will write the core features of our library management system using Microsoft Copilot. This includes adding new books, removing books, and displaying the current list of books using control structures and loops. This step establishes the basic functionality that will be expanded later. Once the core features are in place, errors will arise as you handle book inputs and removal. In this step, we will focus on debugging using Microsoft Copilot. Copilot helps identify and suggest fixes for common issues, like trying to remove a non-existent book or dealing with a full library. Debugging at this stage ensures the system works correctly. After debugging, we'll use Microsoft Copilot to improve the quality and efficiency of our code. This step includes simplifying repetitive tasks, optimizing loops, and improving readability. Copilot will assist in refactoring the code, suggesting best practices to reduce complexity and enhance maintainability. Finally, we'll practice solving advanced coding challenges with Microsoft Copilot. You'll be tasked with extending the system, like adding a search feature for books or limiting how many books a user can borrow. Copilot will help you efficiently solve these challenges and integrate them into your project. This project guides you through the complete coding process from writing the initial code to debugging to optimizing and solving new challenges using Microsoft Copilot. By following this structured approach, you will create a polished library management system that mirrors real-world development workflows.
Welcome to Foundations of .NET Development and Visual Studio Code Integration. In this module, you'll dive into the essentials of .NET, harness the power of Visual Studio Code, and master setting up and managing your projects. Get ready to elevate your front-end and back-end development skills with these powerful tools. We will start by exploring front-end and back-end development in .NET environments, focusing on its role in building robust, scalable applications and enhancing developer efficiency. Next, we'll explore how Visual Studio Code integrates with .NET projects, enhancing your development workflow. Then, we'll examine how to set up your .NET development environment, ensuring everything is in place to start coding. After that, we'll identify the key steps for initiating a new .NET project, from planning to execution. Finally, we'll explore best practices for organizing your .NET projects, focusing on effective file structure and code management. By the end of this module, you'll have the skills and confidence to develop and manage front-end and back-end projects in .NET using Visual Studio Code. Let's get started with Foundations of .NET Development and Visual Studio Code Integration. Have you ever wondered how the apps and websites we use every day come together to create such seamless experiences? There's a whole world behind every button you press and every web page you scroll through. This world is divided into two main areas, front-end and back-end development, each with its own set of responsibilities and challenges. In this video, we will describe front-end and back-end development. Front-end development is the practice of building the visual and interactive elements of a website or web application that users directly interact with. Front-end development is all about what you see and interact with on a website or app. This includes the layout, buttons, text, and even animations. Front-end developers use a combination of HTML, CSS, and JavaScript to make sure everything looks good and works well. Now that we know what front-end development is, let's explore the types of tasks front-end developers handle in their daily work. First, front-end developers structure content with HTML, style it with CSS, and make it interactive with JavaScript. For example, they might build a responsive menu or create a form that checks your information before submitting it. Second, front-end developers often use frameworks like React or Angular to speed up their work. These tools help them build complex features like a search bar or a user profile without starting from scratch. Third, they ensure that websites work across all devices. They adjust layouts, fonts, and images so everything looks great on screens of all sizes, whether it's a phone or a desktop. Fourth, they focus on optimizing the performance of websites by minimizing load times. They compress images and streamline code so users don't have to wait for pages to load. Fifth, front-end developers work with designers to improve user experience. They ensure that navigating the website is intuitive and simple, such as making a checkout process faster or improving layout for better browsing. By handling these tasks, front-end developers create a seamless and visually engaging experience for users, ensuring the website is easy to navigate and responsive across all devices. Now that we've covered front-end development, let's shift to what back-end developers do behind the scenes to ensure the front end runs smoothly. Back-end development is the practice of building and managing the systems that power apps and websites, such as data processing, storage, and application logic. Back-end development is responsible for the servers, database, and logic that make a website function. Back-end developers ensure that all the data the front end needs is processed securely and efficiently. With a clear understanding of what back-end development involves, let's explore the daily tasks that back-end developers perform. First, back-end developers write the code that processes requests, such as logging in or submitting forms. They use server-side languages like Python, Ruby, or Node.js to ensure everything on the server works correctly. Second, they manage databases, which store all the website's data. They write queries to retrieve or update data, such as fetching a user's profile when they log in. Third, they ensure that the system is secure and scalable. This involves protecting sensitive information and designing systems that can handle more users as the site grows. Fourth, Backend developers use frameworks like Django, Express, or Spring to streamline server-side tasks. These tools help them manage things like login systems and data storage efficiently. Together, these backend tasks ensure that the website's data flows smoothly and securely, providing the necessary support for everything the front end delivers to the user. Front-end and back-end development work hand in hand to create a seamless web experience, whether you're seeing a smooth interface or accessing data in the background. Both roles are essential to building the websites and apps that we use every day. Starting a new project from scratch can be overwhelming, much like a chef trying to grow their own ingredients before cooking. Instead of reinventing the wheel, developers can use platforms like .NET, which offer pre-built tools and libraries. This allows you to focus on what truly matters, bringing your unique ideas to life efficiently. Development platforms provide sets of tools that work together like a house kit, allowing you to focus on the unique aspects of your application. In this video, we will learn about the .NET ecosystem, including its significance and different versions. .NET is a platform created by Microsoft that simplifies the software development process by providing a unified set of tools and pre-made code. Originally launched as the .NET Framework, it aimed to address challenges such as using multiple programming languages and managing complex dependencies on Microsoft Windows operating system. The .NET platform offers a wide range of features, making it a versatile choice for various development projects. Initially, it was exclusively used for Windows-based applications, but with the advent of .NET Core and later .NET 5, it became cross-platform, meaning it works on different operating systems. This means developers can now build and deploy applications on Windows, Linux, and Mac OS. .NET's ability to work across different operating systems has made it a preferred choice for developing a wide range of applications, including web, desktop, mobile, cloud, and Internet of Things applications. One of the key features of .NET is its support for multiple programming languages, including C#, F#, and Visual Basic. This flexibility allows developers to choose the best language for their specific tasks. Additionally, .NET includes a comprehensive collection of reusable code and tools, known as the Framework Class Library, which provides functionalities for data access, security, web development, and more. The flexible design of .NET allows developers to include only the parts they need, leading to improved performance and efficiency. .NET also excels in web development through ASP.NET Core, a powerful framework for building modern web applications. ASP.NET Core is known for its high performance and ability to handle a lot of traffic, making it ideal for applications hosted on the internet and those that use small independent services. Furthermore, with the introduction of Blazor, .NET can take advantage of a technology called WebAssembly to run .NET code in a web browser, overcoming a previous limitation of every programming language except JavaScript. Despite its widespread use and robust feature set, .NET often faces misconceptions that can deter potential users. One common misunderstanding is that .NET is only suitable for Windows development, which stems from its early days as a Windows-centric framework. As mentioned previously, with the introduction of .NET Core and now .NET 5 and beyond, the platform has become fully cross-platform, supporting development on Windows, Linux, and Macs. Another misconception is that .NET is outdated and not suitable for modern applications. And this couldn't be farther from the truth, as .NET has evolved significantly, embracing open source principles and modern development practices, including cloud-focused development, small, independent services, and software packaging methods. Finally, some believe .NET is a closed-source ecosystem controlled solely by Microsoft. While Microsoft remains a key contributor, the platform has been open source for years, encouraging community contributions and transparency. It's an inviting and versatile platform for developers of all backgrounds, offering a wide range of tools and libraries for various development needs. In conclusion, the .NET platform offers a comprehensive solution for modern software development, whether building web applications, mobile apps, or complex enterprise systems. .NET provides the tools and frameworks necessary to succeed in today's competitive technology landscape. Imagine you're working on a critical front-end development project, and you have to switch between 10 different pieces of software to get the job done. What if a powerful, all-in-one solution could handle all of the tasks necessary to complete your project? Visual Studio Code can do just that. streamlining your .NET development process. In this video, we will describe how Visual Studio Code integrates with the .NET environment. A code editor is a specialized software tool used by developers to write and edit code. It provides features like syntax highlighting, which colors code based on its structure, making it easier to read and debug. Code editors are essential for developers, especially beginners, because they provide an environment specifically designed for writing and managing code. Visual Studio Code, better known as VS Code, is a popular, free code editor developed by Microsoft, known for its flexibility and extensive features. Visual Studio Code, or VS Code, is more than just a popular code editor. Its lightweight and powerful design means you can write, manage, and debug your code more efficiently, all within an environment tailored to your needs as a developer. VS Code is designed to provide developers with the tools they need to write, debug, and run their code efficiently. It has become a favorite among developers using a variety of programming languages. There are many great code editors out there, like Sublime Text, Atom, and the original Visual Studio. You might be wondering why VS Code stands out among other code editors. The answer lies in its rich feature set, which helps you streamline complex tasks. It has a vast extension marketplace that allows you to customize your environment to fit any project's needs. Plus, with strong community support, you're never alone. Solutions and best practices are always at your fingertips, making your development journey smoother and more efficient. VS Code is great for front-end development, but it can also help you create backends, mobile apps, databases, or simple scripts. Perhaps best of all, it is cross-platform and free. Let's examine the features of VS Code in a bit more depth. When you use .NET with VS Code, your work as a front-end developer becomes much smoother. You can write, test, debug, and deploy your .NET code all in one place without needing to switch between different tools. This saves you time and helps you focus on building your applications. Having a good development environment is crucial because it directly impacts your productivity. An efficient environment lets you work faster with fewer interruptions, which is essential for creating high-quality applications. Another one of VS Code's key strengths is the extension marketplace, which acts like an app store for developers. Imagine being able to instantly add tools that simplify your workflow, automate repetitive tasks, or give you powerful new capabilities. These extensions are designed to make your coding experience smoother and more efficient. For instance, the C# extension for VS Code provides rich support for C# development, including features like IntelliSense, which offers smart code completion based on variable types, functions, definitions, and imported code. It's also true that in today's increasingly remote work environment, that having tools which support cross-platform development is essential. With .NET and VS Code, you have the flexibility to work from anywhere without missing a beat. When you encounter challenges, the vast communities supporting both .NET and VS Code are just a click away, providing resources and support to help you overcome any obstacles. Finally, when you're coding and run into a problem, having access to a large, active community can be a game changer. The .NET and VS Code communities offer a wealth of resources, tutorials, and real-time support, helping you quickly overcome challenges and learn new techniques that can elevate your development skills. Being part of a community means you can access shared knowledge and get help when you encounter challenges. Forums, online courses, and community events are great ways to connect with other developers and stay updated on best practices and new features. Visual Studio Code isn't just another tool in your developer toolkit. It's a powerful, all-in-one environment that streamlines your workflow, making your coding process more efficient and enjoyable. By integrating seamlessly with the .NET ecosystem, VS Code allows you to focus on what really matters, building high-quality applications. Its vast extension marketplace, cross-platform capabilities, and strong community support make it an indispensable resource for developers at any stage. With these tools at your disposal, you're equipped to tackle complex projects with confidence and efficiency. VS Code is an incredibly powerful code editor. It is lightweight yet robust, making it an ideal choice for developers at all levels. Let's delve into some of the key features that make VS Code stand out. Above all, VS Code is flexible and customizable, which allows it to be both lightweight and robust. When you first install VS Code, it has some basic tools for writing code. You can then install additional tools that are tailor-made for the programming languages and workflows that you use. You can also customize your editor itself to fit your style and needs. In this video, we will explore the high-level features of Visual Studio Code. Understanding these features will give you a solid foundation to see how this tool can enhance your development process. Let's dive into one of these powerful tools, the built-in terminal. VS Code has a built-in terminal, so you don't have to switch to other windows to run commands or scripts. You can do it all right inside VS Code. It's especially handy for tasks like building your project, managing your code changes, and running other commands directly from within your coding workspace. Another critical feature of VS Code is its use of modular extensions. Extensions are add-ons that enhance the functionality of the editor. Tools are added to VS Code as extensions. The primary way to get extensions is through the built-in extension marketplace, which is like an app store for coding tools. For example, some extensions can check your code for mistakes, give you shortcuts for common coding tasks, or connect with other services you might use. For .NET developers, there are special extensions that add even more helpful features, making it easier and faster to write and manage your code. Let's explore the C# DevKit extension in a bit more depth. It is a particularly beneficial tool for .NET developers. It includes the C# extension and the .NET install tools, which form a powerful combination. First, let's discuss the C# extension, which powers IntelliSense, debugging, and project management for .NET applications. Think of IntelliSense as a helper that understands the code that you're writing. As you type, it suggests what you might want to write next based on what you've already typed and the rules of the programming language, in this case C#. This is known as code completion. It means you don't have to remember everything yourself. It helps you write code more quickly and with fewer mistakes. You can take code completion a step further using Copilot, an AI-powered tool that helps you write code faster and more efficiently. It acts like a smart assistant, providing suggestions and code completions as you type. Copilot can generate whole blocks of code based on the context of what you're working on, making it easier to tackle complex problems or repetitive tasks. VS Code is also great for debugging, which is finding and fixing mistakes in your code. You can mark specific spots in your code where you want to pause and check what's happening, which is called setting breakpoints. Then you can step through your code one line at a time to see exactly how it runs. You can also look at the values during different parts of your code execution to make sure everything is working correctly. The .NET Install tool is used to manage installations of the .NET SDK, which you need to build and run applications using .NET. It includes everything required to develop software, such as the .NET Runtime, which allows your application to run, and the .NET libraries, which provide pre-written code to help you with common tasks. Additionally, it comes with the .NET CLI, which is a command line interface that lets you create, build, and manage your projects using simple commands that you write in a special tool known as a terminal. It's also worth noting that Microsoft has a special piece of software called Visual Studio as opposed to Visual Studio Code. Visual Studio is a much larger piece of software with virtually every feature you would need to be a productive developer baked into the editor. We're focusing on Visual Studio Code in this course because it tends to be more approachable for new developers and you can easily install it on any operating system. If you work on a large code base, especially in an enterprise environment, there's a good chance you might want to work with Visual Studio. But just know that with the use of extensions, Visual Studio Code can do virtually anything that Visual Studio can. In this lesson, we explored how Visual Studio Code is a powerful, lightweight, and customizable tool that meets the needs of developers at every level. Its built-in features, like the terminal, code completion, and debugging, paired with a vast extension marketplace, make it incredibly versatile. Whether you're working on a small project or managing large-scale applications, VS Code provides the flexibility and tools to enhance your productivity and help you create high-quality code efficiently. Have you ever wondered how top developers streamline their workflow to tackle complex projects effortlessly? Today, we'll follow Alex, a front-end developer, and discover how Visual Studio Code, combined with .NET, transforms daily tasks into a seamless and efficient process. So let's explore how these tools can enhance your development workflow, making every step from coding to development more intuitive and productive. In this video, we will describe the role of Visual Studio Code in .NET development workflows. Visual Studio Code integrates into the .NET development workflow, making everything from project setup to coding and deployment not just easier, but more efficient. Think of Visual Studio Code as the ultimate toolbox for developers. Let's observe how Alex uses VS Code to craft, refine, and deploy projects with precision. For Alex, starting a new project can often be daunting. There are dozens of files to set up, and each with special information that needs to be connected seamlessly. But they have found that VS Code makes this initial setup a breeze. With just a few commands, the basic structure of the project is automatically created, eliminating the tedious manual setups. This efficiency allows Alex to dive straight into writing the code that makes the project unique. After setting up the initial project structure, Alex begins to customize it. They tailor it to their needs by adjusting settings that control how the code runs, and they integrate code from other sources to solve common problems. These customizations ensure that the project is optimized for efficiency and tailored to their specific goals. After integrating new libraries and code changes, the next critical step is to track these modifications. Alex is worried that as they change their code, they might break something or lose their progress. So after integrating new libraries and code changes, they want to keep track of what has changed. And this is where VS Code's built-in Git integration comes into play. It provides version control, allowing Alex to easily manage changes and maintain comprehensive history of the project's evolution. This way, they can always revert their code to a previous version if something breaks, and they never risk losing all of their hard work. It also makes it much easier for Alex to merge any changes they make to their code with changes made by other members. With version control ensuring all changes are tracked, the next step is to test these changes in real time. Alex does this by starting a development server directly from their terminal within VS Code, allowing the application to run locally. This setup lets Alex view the application in a browser without switching context, helping to catch issues early and enabling quick iterations. As Alex delves deeper into the project, VS Code's coding features become indispensable. IntelliSense provides smart code completions, reducing errors and speeding up the coding process. Similarly, debugging tools enable Alex to pause the program's execution, examine the code line by line, and efficiently identify and fix problems. As Alex codes, ensuring that the code performs as expected is crucial. And this is where testing comes into play, and VS Code makes writing and running these tests seamless. By using built-in tools, Alex can write tests, execute them directly within the editor, and receive immediate feedback. This streamlined process helps in quickly identifying and fixing issues, ensuring the application remains reliable and bug-free. Once the code is thoroughly tested and reliable, the final step is deployment. VS Code streamlines this process with built-in tools that let Alex package and deploy the application directly to a production server. This streamlined deployment process ensures that the application is up and running quickly, with the ability to monitor its performance and make necessary updates efficiently. Integrating VS Code into the workflow brings tremendous value to Alex's development process. As Alex becomes more comfortable with these tools, it's clear that VS Code boosts productivity and makes the entire development process much more enjoyable. In today's video, we will walk through the process of installing the .NET SDK. Installing the .NET SDK will allow us to run .NET code, use .NET libraries, and explore the .NET command line tool. We will walk through installation of Windows, but the process on Mac is quite similar. Same for Linux. In this video, we will explore how to install the .NET SDK. The first thing you will want to do is download the appropriate installer for your operating system. You can find the installer at https://.net.microsoft.com/download. It should automatically detect your operating system, and you should see the correct installer listed here. In this case, it's the ARM64 installer, which is what I need. But if you need a different installer, you can click this link right here, the all.NET 8.0 downloads, and this will give you other options. I will go ahead and click this to start installing it. And this should download. And you can see here, I had downloaded this previously, but we'll go ahead and open up that file. And if you don't have it open here, you can navigate to where you downloaded that in your file system and open it from there. So we're going to go ahead and click install. And you're going to want to say yes to allow it to make changes to your device. And you are just going to wait for this to do its thing. It'll take a few minutes sometimes, depending on how fast your computer is. Now that that has installed, you should see this list of resources. You can look here for the .NET documentation, the SDK documentation, release notes, tutorials. If any of that excites you, you can go ahead and click those notes, but we will be covering most of this material in the course, so you can just go ahead and keep listening. So we'll go ahead and click close here. And the next thing you're going to want to do is check to make sure that .NET installed. So you're going to want to open a terminal application. Now, just about every operating system has a terminal now. For a long time, Windows just had PowerShell, but now you can access, you see here, PowerShell through Windows Terminal. So Mac has a terminal, Windows has a terminal, Linux all have a terminal. So all a terminal is a special piece of software that allows you to interface with your computer and run different applications by using text codes. And so in this case, you can type into this prompt here, and you should see this sort of flashing indicator here. If you don't, it means you're not actually in. You can see here I just clicked out and I'm not clicked in. So if I type, nothing will happen. But now if I click back in, there's that indicator again. And all you're going to do is type one word, no capitalization, .net, D-O-T-N-E-T. Anything different than that, and this will not work correctly. Then hit enter, and you should see this usage message. So this is telling you how to use the command. You would not see this if you actually didn't have it installed. If you didn't have it installed, you would see something like this. So I'm going to misspell the name, and it's going to say, that is not recognized as a commandlet, a function, a script file, or an operatable program. So that means that this is not actually a piece of software that's installed. So if you typed in .NET and you saw a message like this, something went wrong. And what you're going to want to do is go ahead and restart your terminal and then try running the command again. And if that doesn't work, go ahead and restart your computer. And if that doesn't work, go ahead and retry this installation process one more time. Now that you have the .NET SDK installed, we can go ahead and install Visual Studio Code. So I have another tab here open, and what you're going to want to do is navigate to this URL. This is code.visualstudio.com/download, and then click on the correct installer for your system. In this case, I'm looking for Windows 11. It looks like this will work on the x64 and the ARM64, which is what I am working on. So you can go ahead and click that, and it will start you here with your download. You will click that download once again, and this time around, you're going to want to accept the agreement. Going to click next here if you like the location. If you don't, you can move it somewhere else, but I find the defaults tend to be really good, especially if you get lost, because it will be in a place that the internet knows about. So let's go ahead and check these next options here. Now the first two options I wouldn't worry about, but these last two you definitely want to leave clicked. So this first one, register code, is an editor for supported file types. This means that Visual Studio Code will be able to open different programming types of file directly from that file. So it's like if you have a spreadsheet, it will open directly into Sheets or into Microsoft Excel. So if you try to open a code file, it will open directly in Visual Studio Code. You can also add to path, and this is important. So this will allow you to run Visual Studio Code from the terminal like we just showed, sort of like .NET. You don't need to do this, but I highly recommend it. It's really handy to have around. So with those two, we will go ahead and click Next and Install. Once this is finished installing, you can go ahead and launch Visual Studio Code by just leaving this checked, but I'm going to go ahead and close that so I can show you how to get to Visual Studio Code if you haven't already opened it up. So I will go ahead and type in Visual Studio Code, and that will bring up the best match here is Visual Studio Code. Now both Linux and Mac have sort of search options similar to this. You can also type in VS Code. That tends to work on most operating systems. And now that we're opening here, you can see this is Visual Studio Code. So you have now installed Visual Studio Code and the .NET SDK, and those are the first two critical steps in starting to work as a .NET developer. Now that you have Visual Studio Code installed, let's go ahead and configure the working environment. In this video, we will learn how to configure the .NET development environment. When you install Visual Studio Code, you'll see a window like this. And so there's some resources here on the right for getting started. I highly recommend clicking these Learn the Fundamentals or Getting Started with VS Code. And this will give you a handy list of things that you can customize. But first, let's discuss how to navigate in Visual Studio Code. You'll see your main working area here with tabs, sort of like a web browser, where you can close these, move these, and even do a split pane where you have them side by side. Then at the top here, you have a navigation bar that allows you to do things like save files, change your selection, work with the terminal, and run your code. Over here on the left, you have the File Explorer in this sidebar menu. You also have Search, Source Control. You can run and debug your code. And notice you have Run and Debug down here, and you also have Run and Debug up here. Additionally, you'll also see hotkeys next to nearly everything. So there are multiple ways to get to what you're trying to get to through different menus or hotkeys. I highly recommend taking a minute to learn a few hotkeys for skills that you're using constantly. Don't try to learn every hotkey in the editor. There are many of them, but there are some hotkeys. for navigation, for searching for files, for opening new files, and formatting your code that I find myself using constantly. As you find yourself doing something repeatedly, go ahead and see if there's a hotkey that you can use for that. Now that we've covered the basics of navigation, let's explore how you can personalize your environment. Visual Studio Code is highly configurable. You can make endless changes to your development experience, and you will surely continue fine-tuning your editor experience to meet your needs. That said, I recommend you stick with the default settings for most things. Heavily customizing your editor can slow down performance and make it harder to solve any issues you run into with a quick web search. But you can do things like change your theme, add support for different languages, which we will do. You can fine-tune other settings, you can sync across different devices, and you can use the command palette. The command palette is one of the best ways to navigate around Visual Studio Code. And if you click this option here, you can see Unlock Productivity with the command palette. And there's a very important hotkey here. So if I hit Control, Shift, and P, it will open up this little prompt. Now this is going to look a lot like a terminal, and that's because it works similarly. I can type in a particular option I want to use, and this is a command I can run. I can close window. I could call this directly with a hotkey, but if you don't know how to do something, you have this huge list of commands that you can quickly search for the way to do something. And it is an absolutely huge list of commands. And as you add more extensions, you can add additional commands into this list. The next thing we want to do is install some extensions, and you can see here you can do this from the command palette, but I want to show you how to do it through the menus. So over here on the left side is the extensions button, and you're going to click that, and this is where you will install and manage extensions. Perhaps the most important extension to add is the C# Dev Kit for working with .NET. Now I can see it right here, but if you don't see it at the top of this list, you can type in C# Dev Kit, and that will do a quick search for it. And you can click install directly here, or you can also click on this listing to see all of the information about this extension. So you can see a C# Dev Kit, who made it, how many times it's been downloaded, how many stars does it have, and you can also see more information along here. This is really handy, especially once you've installed it, because it'll tell you the types of things you can do. So I'm going to go ahead and click install here, and you'll see this go a little bit darker. And we're going to wait a second for this to install. And once that extension is installed, you should see this installed check mark, and you should see the disable and uninstall buttons. If you ever wanted to remove the extension, you would use these, or if you want to disable it, you can use this. You may also find a time when the extension is having troubles and not working appropriately. There will be an option in here to restart that extension. And with that, congratulations! You now have all the basic tools you need to be a .NET developer. You have the .NET SDK, you have the C# Dev Kit installed in Visual Studio Code, and you are ready to rock. As you move through your journey as a developer, you may want to add additional extensions, but this simple setup provides the backbone for millions of .NET developers around the world. In the past, project creation could be a real pain. You have to make multiple files in the right directories and put the same boilerplate information into every file. Luckily, modern dev tools have made it much easier to create new projects, and .NET is no exception. Using the .NET CLI or the command palette in VS Code, you can quickly set up basic .NET projects that you can customize to meet your needs. In this video, we will build an understanding of the initial steps to create a new .NET project. We will walk through the process of creating a project using Visual Studio Code. If you are already familiar with using the command line, you can also create projects using the .NET New command. Let's begin by creating a new project. To create a new project, you can do it through this button here in the File Explorer if you have the C# Dev Kit extension installed, but I prefer to do it through the command palette. The key code there is Control-Shift-P, that's the hotkey, and you can type in .NET New Project, and that will show you an option here for this command. So if you click .NET New Project, you'll see here a list of the different types of projects you can create. Now there's a whole long list of these here, and so the main ones you're going to be interested in for doing web development are these ASP.NET Core ones and the Blazor ones, but there are a bunch of different types of projects. We're not ready for web development yet, so we're going to create a console app, and so this is an application that will work in the terminal. So I will click Console App, and then I will select a folder where I want to put that. I will put it in my Documents, And I will call this project console app. Hit enter. This will have a default folder that will be created here. For console app, you could put this anywhere you want to, but I find having it in a folder named the same thing is quite useful. This will go ahead and create a bunch of folders and files. Now you're going to want to trust the author of these files or folders. So this is your computer programmatically building these files. So I'm going to say, yes, I trust the authors. And that will allow me to access these files. So these have now been created by .NET. If you don't see the folders over here, click into the File Explorer. You might be in one of these different menus. As I mentioned earlier, we create several files here. A lot of these are really complicated and would take you a long time to build manually. But at the heart of them is this program.cs file. This is where you will write your custom code. You can see here we have a single line of code. It's console.writeLine hello world. This line of code calls the console.writeLine function, which is a special function that writes a new line of text in the terminal. In this case, it's taking a single argument, which is the text that should be shown. In this case, hello world with an exclamation point. Because this is a terminal app, it makes sense to run this using our terminal. So we can use the .NET CLI to run our program, and all we have to do is type .NET run followed by the name of our program. In this case, we'll type /program.cs. A handy trick here is if you type in .NET Run, then the letter PR, and then hit Tab, it will automatically fill, and that makes it much easier. So again, you can type /program.cs or type /PR tab, and it will auto-complete that for you. And we can go ahead and run that program. And if this is the first time you've run that, it's going to take a second because it's actually building the code that will run that function. Remember, C# is a compiled language. The result of this program is you should see hello world in the terminal output. You can see it right here. So this is a text that is actually created by our code. We can go ahead and make it something different. So let's make that say hello.net. And I will make sure to go ahead and save that. If you don't, you won't see the changes. I'm using the Command S hotkey there. And let's run that one more time. And this time you see hello.net. By following these steps, you've officially written your first .NET code. This is an important milestone as you continue your journey towards becoming a developer. Well done. Imagine you've just laid the foundation for a new building. Before adding walls and windows, you need to ensure the blueprints align perfectly with your vision. In the same way, configuring the initial settings is a crucial step when starting a new .NET project to ensure everything runs smoothly. In this video, we will configure initial project settings. The first place we will search is our csproj file. The name of the file will match the name you specified when you built the project. This is a special file that defines how your project should handle running, testing, building, and other types of configuration. We have a relatively basic setup here, so this is quite simple. You may see much more complicated csproj files in the future. The data in a csproj file uses XML, a format for organizing and storing data in a text format that is both human readable and machine readable. The text between angle brackets is called a tag. Tags come in pairs, an opening tag and a closing tag. The closing tag begins with a backslash. Some information goes between the tags. You can see here you can nest tags in other tags. This output type tag has a value inside that is just simply text, in this case exe. Tags can also have parameters. The first tag we encounter here is the project tag with the attribute SDK equals Microsoft.NET SDK. So this is what's setting metadata. So this isn't actually the data that's held inside the tags. This is sort of data about that data. So this is another way that you can encode information in XML. You can put values between the tags. You can have these attributes that live within the tag itself. This tells a tool called MS Build what kind of project you're working on. If this is a web project, you might find .sdk.web instead of just .sdk. Or if it was a desktop application, you might find sdk.windows desktop. Another important piece of information is the target framework, which in this case is Net 8.0. 5.0, which means this uses .NET version 8, which is the latest stable version as of the recording of this video. If you wanted to use a different version of .NET, this is where that would be specified. In the future, it will likely be .NET 9 and beyond. Using a tool like C# DevKit to scaffold out these files has given us a great starting point. You often won't need to worry about modifying your CS proj file. It's useful to know what's in here, but don't worry too much about knowing exactly what all of these things do. If you ever need to find something specific, you can research it later. So that is the first place where you will see configuration in a .NET project. Next, we might want to add packages. Packages are pre-written code that you can utilize in your project. Packages in .NET ecosystem are added by a piece of software called NuGet. So if we look here in our program CS file, you'll see that we have a relatively basic console app. It just has this single console.writeline with hello world. I like what we have so far, but I'd like to change the color of the output text. To accomplish that, let's use a package called Pastel. If we open up the command palette, let's see if we can find a way to add a NuGet package. NuGet is spelled N-U-G-E-T, so let's type add NuGet to see what's here. Hey, there's the command we want right there. NuGet add NuGet package. The package is called Pastel, so let's type that into this search bar and hit enter, and it will run a search for Pastel. And here is the first one we want, this Pastel option right at the top of the list of returned packages. Next, it will ask us to select the version. At this point, 5.1.0 is the latest, but if you want a different version, or if in the future there's a newer version, you can go ahead and select that. If you're following along with this code, it's best to use the exact same version in case the code changes. Now, if we go over to our CS proj file, you should see something new. This item group with package reference include Pastel version 5.1.0. This is showing us that we have installed the Pastel package and that is a dependency of this project. So that means that is a piece of code that our code is now going to rely on. First, we'll go into our program.cs file, select just after the closing double quotes. I'll type in period, then capital P-A-S, and you can see here it's starting to autocomplete to Pastel. So I'm going to go ahead and click that, and I could just type this in, but if I click here, it's going to do something really useful. If I click that, you'll see it added this using Pastel. This is going to provide us with the import for this package. That means that our code now understands where Pastel is coming from. It's coming from an external package or library. Next, let's open up some parentheses, and if I type in color dot green and mind the capitalization here, you need a capital C with color and a capital G with green, or this code won't work correctly. Again, we can use IntelliSense here. It's showing us all of the different options for colors that start with green or have green in their name. In this case, I'm going to choose light green, but you can choose any color you like. Again, make sure to use capitalization, otherwise this code will not work correctly. Now, if I save my file and open up a terminal again, now if I type .NET run and then add my program file to the end of that, so .NET run period /program.cs and hit enter, you should see the output here, which is hello world now in light green instead of that light gray color. Excellent. Our project is really coming along, thanks to our knowledge of the CS proj file and adding an external package like Pastel. Imagine you've just finished coding your first .NET application. What's next? How do you ensure it's ready to run and distribute? Let's discuss what happens when we run and build our code. In this video, we will run a new .NET project. We showed how to run our application using the terminal, which makes sense because it's a terminal application. But what if we wanted to make a different type of application, like a web application or Windows application? You can still run them from the terminal, but there's also a handy feature built into VS Code that will let you run your application through the graphical user interface. You can see here that we can click Run on the left side of the screen, and that will allow us to run and debug our code. So if I click Run here, I can go Run and Debug. It'll ask us what language, and in this case I'm going to say C#. and the C# console app. This will be my launch configuration. And now our application is running. Now this will take a little bit the first time you start this application. Because this is a terminal app, it automatically opens the terminal. And here is our output. You see the hello world. Let's talk briefly about what happened behind the scenes when we ran our code. C# is a compiled language, meaning that the code that we write needs to be converted into instructions that a computer can execute before it can be run. This conversion process is often referred to as building the application. When we use the .NET run command, it compiles or builds the application first and then runs it. That's what's happening behind the scenes when we use the graphic user interface to run our code. After the application is built, the compiled output is placed in the bin folder. So if we go back to the File Explorer and look at bin, you'll see this is now full of files. This is the code that was run to create this terminal output. Typically, you will just want to run your application, but sometimes you may want to build it without running it. To do this, we can use the command palette again, and we can type in build, and you should see an option something like this where it says .NET:build. That's what we're looking for. That is the build command. And if we hit build, it will once again go through that same process, but this time we won't see that same terminal output. And that's because our code is built, but not run. We could also accomplish the same thing by opening up a new terminal and running .NET build. This will run the same command. And you can see here that we have now built our project once again. Not only can we build our project, but we can also remove it. If you ever want to remove your compiled code, you can use the .NET clean command. You could also do this from the command palette, but in this case, we'll go ahead and use the command line. And there we go. You have seen we now have an empty folder up here. That's because all of our binaries have been removed. It does leave some of the temporary files in OBJ, but our binary outputs are now clean. You would want to clean your code if you accidentally created files that wouldn't run. Or maybe you have some outdated code that you don't want hanging around. Sometimes your cache gets corrupted. And don't worry that you will lose your code when running .NET Clean. It only affects the bin folder and not your C# files. You've successfully run, built, and cleaned your first .NET application. Understanding how .NET handles code execution and project management is essential for ensuring your application is ready for further development and eventual distribution. Just like organizing a kitchen makes cooking more efficient, understanding your project structure will streamline your coding process. In this video, we will explain project structure and file organization in .NET. We will start by discussing our program.cs file, our csproj file, and the bin and obj folders. First, program.cs is the entry point for our application. This is the file that we run when our application starts. We could have many other files that contain code that gets run by the code in the file, but this is where execution begins. This is the heart of our custom application logic. Not all types of .NET projects use the program.cs file as their entry point, which is part of what makes scaffolding .NET projects so great. With some experience, when you create a new project, you should be able to examine the generated files and determine which file is the entry point. You can always use a web search or AI tool to find out the name of the entry point for different types of .NET projects. Now that we know where our application starts, let's explore the csproj file to determine how the project is configured. We discussed the csproj file in a previous video. It defines your project's settings, dependencies, and configuration. It tells the .NET Build system how to build your project, what files are included, which NuGet packages and libraries your project depends on, and other configuration details. This is a relatively simple csproj file. When you create your own projects, you will likely have many more dependencies from NuGet and linked projects that you create. You can also define settings that affect how your project is built. Next up is the bin folder. We mentioned that this is where our compiled code is stored. If we open up consoleapp.exe, we're going to see a warning. And that's because this is a binary file. But let's go ahead and open this up anyway, because I want to show you what's in here. We're going to open this as a text editor, and you'll see here why we usually don't open these. This looks kind of scary, but all that's happening here is this looks like a bunch of gibberish. And that's because it's not meant for us. It's meant to be read by our computer, and VS Code is trying to interpret it as text in this case, which results in this funny looking output. The executable file is the file that is executed when we run our application. And the DLL files in here are other pieces of code that are executed by our application, but not directly by the end user. We have two DLLs here, Pastel and consoleapp.dll, which is the code we wrote. It's turned into a library run by the executables alongside Pastel. Now that we've determined where our compiled code goes, let's examine the OBJ folder. Now, the OBJ folder is involved in the build process. You usually don't need to interface with the OBJ folder, but it's helpful to understand why it's here. This directory stores intermediate files generated and used during the build process. These files are not the final output, but are necessary to compile your project into its final form. If something goes wrong in your build process, you might check the files in this folder to determine what's happening. And now you have all the essential information you need to navigate a simple .NET project. Different types of projects will have other files, but all .NET projects will share these core files and directories. Imagine you're building a .NET project where users can upload pictures of their pets. As the project grows, managing the code becomes challenging without a clear structure. Just like a well-organized library makes finding books easy, organizing your code into structured files and folders helps keep your project manageable and efficient. In this video, we will describe best practices for organizing files in a .NET project. We've mentioned that .NET automatically creates folders like bin and OBJ to manage build process. But beyond that, you have a lot of flexibility in organizing your files. While there are many ways to do this, the goal is to make the code easy to understand, work with, and maintain. Good code organization helps everyone on your team, including you, follow what's happening. Like reading a book, code must be clear because it will be read more often than written. One method of separating code is called separation of concerns. This design principle in software development involves dividing a program into distinct sections, each responsible for a specific aspect or functionality of the application. As the project grows, you also might need folders to keep everything organized. You can organize by features or by layers. Let's return to our pet photo project. The app's main parts are the users, pet pictures, and comments, which could be called features. You could organize the code by creating separate files for each feature. However, each feature has code that performs different tasks, such as storing data in a database or showing it on a screen. So you might split the code for each feature further, with files for database work, display work, and the intermediary code that connects them. For example, organizing by features means all user-related code, database, display, etc. stays together. Organizing by layers means grouping code by its role, like having separate folders for database code, display code, and so on for all features. There's no one right way to organize. It often helps to follow examples from starter projects or community projects. Also, if you plan to reuse code in other projects, consider putting it in a folder that can easily be copied or loaded as a reusable module. SRC, pronounced source, is a common name for the folder that holds uncompiled code in a project. Now that we've organized our files, the next step is to ensure they are named in a way that enhances clarity and maintainability. Naming is important because it helps others and your future self understand what code does. In .NET, a common practice is using a combination of Pascal and camel case for file names and variables. In Pascal case, words are combined, but they each start with a capital letter. Camel case is nearly identical except the first letter is lowercase. In C#, most identifiers such as class names, methods, and properties use Pascal case. Camel case is typically used for private fields, method parameters, and local variables. This distinction helps maintain clarity and consistency within C# code. I also want to point out that this is a convention and not a rule of the C# syntax. These naming conventions are a hot topic in developer forums, but choosing clear and descriptive names is more important than following any specific naming convention. Naming is a skill that requires thought. The goal is for another developer to understand what your code is doing just by reading it. For example, a variable named num is vague and unclear. What number is it referring to? A better name might be user age, which immediately tells you it's related to a user's age. Even though shorter names are quicker to type, longer and more descriptive names make your code easier to understand. If the variable is meant to represent the age of a user's account rather than their actual age, a name like user account age would be even more precise. As your project grows, you might need to reorganize or improve the code, a process called refactoring. Refactoring is improving the structure and readability of existing code without changing its behavior. Refactoring aims to make the code cleaner, more efficient, and easier to maintain. A common saying is, make it work, make it right, make it fast. Focus on getting a simple version of the code working, then improve it over time. Don't worry about writing perfect code from the start. It's more important to have something that works, which you can refine later. Now that your code is organized into a good file structure and the code files themselves are well written, it's helpful to think about documentation. One way to do this is by including a README file in your project. This is an external file which provides an overview of the project and a valuable guide for anyone new to the code. You can also document code by adding comments, which are inline text in the file that isn't interpreted as code. They are there to be read by humans rather than computers. There are different opinions on how to approach documentation. Some developers believe in using lots of comments to ensure the code is easy to understand. However, comments can become outdated if the code changes, leading to confusion because the comments no longer accurately reflect the code. On the other hand, some developers avoid comments altogether, focus on writing code that is so clear that it explains itself. While this approach works well in many cases, there are times when code alone can't fully capture the reasons behind certain decisions. A balanced approach is often best. Write your code as clearly as possible, but don't hesitate to add comments where extra explanation is needed, especially for important decisions. Keeping your code organized and well documented makes it easier for others to work with it and for you to revisit it later. Clear, understandable code is critical to being a successful developer. As you have discovered, mastering front-end development with the .NET environment is essential for building scalable applications and optimizing your workflow. These skills are key to successful development, from integrating Visual Studio Code to setting up projects and managing your code effectively. We began by examining front-end development within the .NET environment, highlighting how it supports creating scalable, high-performance applications and improves development processes. Then we examined the integration of Visual Studio Code with .NET projects, demonstrating how it streamlines the development workflow. Next, we focused on setting up your .NET development environment, ensuring you have everything ready to begin coding. Then, we outlined the essential steps for launching a new .NET project, covering everything from initial planning to final execution. And finally, we reviewed the best practices for structuring your .NET projects, emphasizing efficient file organization and code management techniques. Effective front-end development within the .NET environment is crucial for creating scalable and high-performing applications. Mastering the integration of Visual Studio Code, project setup, and efficient code management will greatly enhance your development process and overall project success. Congratulations on completing foundations of .NET development and Visual Studio Code integration. Welcome to Applying Programming Foundations. This module will deepen your understanding of the fundamentals of programming concepts and help you integrate them effectively into your practical projects, building a strong base for more advanced development. To reinforce your foundational knowledge, we will begin by reviewing essential programming concepts, such as variables, data types, control structures, loops, methods, and pseudocode. Next, we will integrate logical thinking with these programming fundamentals, enhancing your problem-solving abilities. Then, we will introduce basic debugging techniques and tools equipping you with the skills to identify and fix errors in your code. After that, we will practice writing simple programs in C#, applying everything you've reviewed to build functional applications. And finally, you will create a project that combines all of these concepts and debugging techniques, giving you practical experience in applying your skills to a complete development task. By the end of this module, you'll have the confidence and skills to apply key programming concepts in practical projects and effectively debug and build applications in C#. Let's get started with applying programming foundations. Programming is like learning a new language, one that allows us to communicate with computers and bring our ideas to life. Just like any language, there are core elements that we must understand to express ourselves effectively. In programming, these core elements include variables, which store information, data types, which define the nature of that information, and control structures, which manage how that information is used. Mastering these fundamental concepts is essential. They form the foundation of everything you'll create as a developer. In this video, we will summarize key programming concepts. One of the most important concepts in programming, and the one that started it all, is Boolean variables. These variables allowed computer scientists to actually make computers think logically as humans do. In C#, a Boolean variable is a type of variable that can hold one of two values, true or false. These values are commonly used to represent binary states such as yes or no, on or off, true or false. There you have it. Simple, but fundamental and powerful. Imagine you're developing a video game and need to track whether a player is alive or not. A Boolean variable could indicate whether the player is alive. To do this, we write bool to indicate it is a Boolean variable, then isPlayerAlive, which is the variable's name. We assign the value of true using the equal sign and writing true. Boolean logic in programming uses true-false values to perform logical operations like and, or, and not, which are crucial for making decisions in your program. The following are the basic operations you can perform in Boolean logic. The AND operation returns true only if both conditions are true. The AND operation is a logical operation that evaluates multiple conditions. It will only return a result of true if every condition being checked is also true. If any one of these conditions is false, the result will be false. The AND operation is particularly useful when you need to verify multiple criteria meet at the same time. For example, if you want to ensure that a user is both logged in and has the appropriate permissions, you would use the AND operation to check both together. In the C# programming language, the AND operation is represented by two ampersands. When you use ampersand between two conditions in C#, it checks whether both conditions are true and only returns true if they are. For example, let's say that in our game, a player is ready when it is at full life and it is at full stamina. You'd use an AND operator, ampersand, between the two variables, is it full life and is it full stamina. The operation returns true only if both conditions are met. Let's say these are the bars of life and stamina of the player. Here, both bars are below full, so the operation to determine whether the player is ready returns false. Even if one of the bars goes up to the top at full, the players are still not ready. The operation keeps returning false because one of the variables is false. It is only when both conditions are met that we have a player that is ready to play. There's another Boolean operation that helps you calculate if at least one of the values is true. The OR operation is useful when determining if at least one of several criteria is satisfied. For example, if you want to allow access if a user is an admin or has a special pass, you would use the OR operation to check if at least one of these conditions is true. In the C# programming language, the OR operation is represented by the two vertical bars. When you use vertical bar between two conditions in C#, it checks whether at least one of them is true, and if so, returns true. While AND requires both conditions to be true, OR is more lenient, returning true if just one condition is met. Let's see how OR works. In our example video game, you might check if a player is defeated and thus not ready to fight by checking if he is either at 0 life or 0 stamina. This operation returns true if the player is 0 in life, stamina, or both. Let's say these are the player's life and stamina bars. Right now, they are both at 0, which means that the player is defeated, of course. But since this is an OR operation, the player is defeated if just one of the variables is true. Even when the player has some life, in this example, the player is still defeated because his stamina is at 0. It is only when both variables are false that the operation returns false. This is when the player has a little bit of both, life and stamina. In summary, AND and OR operations work on the values of two Boolean variables. If both variables are true, then both operations return true. However, if one variable is true and the other one is false, then AND will give you false, but OR will be more lenient and give you true. And finally, if both are false, then the result will be false for both operations. The NOT operation is a logical operation that flips or inverts the value of a Boolean. If the Boolean is true, applying the NOT operator will make it false. And if the Boolean is false, the NOT operator will make it true. The NOT operation is particularly useful for toggling states in programming. For instance, if you have a feature that needs to be turned on or off, the NOT operation can switch between the two states. If the feature is currently on, true, applying NOT will turn it to false, off, and vice versa. In C#, the NOT operation is represented by the symbol exclamation point. When you place exclamation point before a condition in C#, it inverts the condition's Boolean value. For example, if you have a condition is logged in that is true, then writing exclamation point is logged in will evaluate to false. As another example, in the video game, you might want to know whether the player is not defeated. In that case, you'd use the NOT operator exclamation point before is defeated variable. After understanding how to store and manipulate data with variables and Boolean logic, the next step is learning how to control the flow of your program. This is where control structures guide your program's decisions and actions. Conditional statements are like decision-making tools in programming, helping guide what a program does next based on specific conditions. For instance, think about the part of a game where there is a door and it only opens if the player has a key. But what if the player doesn't have the key? That's where an else statement comes in, offering an alternative action. If the player doesn't have the key, then perhaps the game displays a message saying the door is locked. And what if you have multiple options? What if the rules state that the player can use different potions? This is similar to a switch statement, which checks a variable against multiple values. A switch statement lets you choose different actions based on several predefined conditions. Loops are another essential concept in programming. They allow you to repeat a set of actions until conditions change. Imagine our hero needs to sell every item in his inventory. While we could go one by one on each and every item and sell each of them, it'd be more concise and computationally efficient to just write some code that repeats in a loop for every item the hero has. A for loop is ideal here, letting us iterate through each item individually. Similarly, if our hero must continue attacking enemies as long as they keep spawning, a while loop would be the right choice, allowing the code to run until no more enemies appear. This loop keeps running until the condition, like the spawning of new enemies, no longer holds. In this video, we have summarized key programming concepts. Understanding the fundamentals of programming such as variables, Boolean logic, conditional statements, and loops is crucial for any developer. These concepts are not just building blocks, they are the foundation upon which more complex programming skills are built. By mastering these essentials, you're preparing yourself to tackle more advanced challenges and create more sophisticated programs. Remember, like any new language, programming becomes easier with practice. So keep experimenting, keep coding, and soon these concepts will become second nature. Imagine trying to solve a complex problem without breaking it down into smaller, manageable steps. It would be overwhelming. In programming, pseudocode and methods help us do just that. Pseudocode is a powerful tool that helps us plan and think through our logic before we even start coding. On the other hand, methods allow us to organize our code into reusable blocks, making our programs more efficient and easier to understand. In this lesson, we'll explore how methods structure our code and how pseudocode serves as a blueprint for solving programming challenges. Pseudocode is a plain language description of the steps in an algorithm or code structure. Pseudocode serves as a bridge between your initial ideas and actual code, allowing you to outline the flow of your program in simple terms. When writing pseudocode, the key is keeping it straightforward, concentrating on the core logic rather than getting bogged down in details. Let's look at how to write pseudocode. To write effective pseudocode, keep it simple, focusing on the main logic. For example, if you were writing pseudocode for a method that accelerates a car, you would write initialize car, accelerate car, and then in accelerate, you would write if gas is greater than 0, increase velocity by 1, you'd return the velocity, display an animation, and then it ends. Pseudocode allows programmers to focus on the logic without getting bogged down by syntax. While pseudocode helps you concentrate on the logic of your program without worrying about the syntax, methods bring that logic into action with your code. Methods are essential tools that allow you to organize and reuse your code efficiently, applying the logic you've planned out in your pseudocode directly to your program's functions. Methods are blocks of code designed to perform a specific task. Think about a method as one of your teammates in a significant event planning. They will have a set of responsibilities that they will enact once you give them a call. Methods help programmers break down complex problems into manageable pieces. For example, imagine we're building code for a car in a video game. In this scenario, you will use a method to accelerate the car by calling it. You would have to say accelerate and the car will do so. Declaring a method involves specifying its name, return type, and parameters. For example, this method, called accelerate, could be used to accelerate a car in, let's say, a game or simulator. A method can have parameters to specify its intended behavior. For example, we added a gas parameter in our car video game, which tells the method how much to accelerate. Parameters allow methods to be flexible and reusable for different inputs. Methods must define a return type. Return types specify the type of value a method will return. This can be useful when you want the method to inform the caller about something. For example, if we want to know the car's final velocity, we can use an int return type, which will tell us the car's actual velocity after acceleration. To call a method, you call it with the appropriate arguments. In this example, we just use its name, accelerate, passing the appropriate arguments for how much gas we are inputting, 10 for this example. In this video, we've seen how methods and pseudocode work hand in hand to simplify complex programming tasks. Just like the method to accelerate a car in C#, methods in your code encapsulate functionalities, making your programs more organized and reusable. Pseudocode helps you plan these methods clearly, allowing you to focus on the logic before diving into the coding details. By mastering both, you can build more efficient, maintainable, and understandable programs, much like how clear instructions can make driving a car smoother and safer. Imagine you're trying to solve a puzzle. You have all the pieces, but putting them together requires careful thought and a step-by-step approach. Logical thinking in programming works in the same way. In this video, we will explain the principles of logical thinking in programming. Logical thinking in programming refers to the process of applying systematic reasoning to define a problem and arrive at a solution. Within the context of programming, developers most frequently use two primary logical thinking skills: deductive reasoning and problem decomposition. Let's start with deductive reasoning. Deductive reasoning is the process of drawing specific conclusions from general premises. Let's see how this works in programming. Deductive reasoning starts with premises. A premise is an assumption or fact used to draw a conclusion. Programmers use deductive reasoning to debug and fix issues more efficiently. For instance, let's assume you're debugging a system and discover a function that's causing unexpected behavior. You would approach the problem by working from two primary premises. The first is that all bugs cause unexpected behavior in the system, and the second is that this function is causing unexpected behavior. On the basis of these premises, you could draw the conclusion that this function must contain a bug. Programmers use deductive reasoning to gain a high-level understanding of how a problem should be solved. Once they have a high-level view of the problem, they can define a logical step-by-step approach for solving it. Next, let's look at the most commonly used step-by-step approaches to problem solving in programming. When you're presented with a problem, you most likely evaluate it and begin to strategize how you're going to solve it. A common approach is to look at a larger problem in terms of its constituent parts and make it easier to solve. This is called problem decomposition. There are two main approaches to problem decomposition: top-down and bottom-up. The top-down approach is a method of problem solving that begins with a broad overview of a problem and breaks it down into smaller, more manageable parts. The top-down approach is useful when you have a clear overview of a problem, but need to break it down to make it easier to manage. By using the top-down approach, you can decompose the problem into smaller atomic tasks that are more easily addressed. For example, if you're building an e-commerce website, you might focus on a high-level problem such as designing shopping cart functionality. Next, you would break down this functionality into smaller components, such as adding items to the cart, updating quantities, and processing payments. You would then continue by breaking down each of these into even smaller components, more specific items, until you arrive at manageable coding tasks. The top-down approach helps developers go from a big idea to specific tasks when developing software. but it's not always ideal in every situation. Sometimes the developer needs to gather more information when they're debugging or take a modular approach to software development. In these cases, they may prefer bottom-up approaches to solve the problem. Let's explore the bottom-up approach next. The bottom-up approach is a method of problem solving that starts with the most basic elements and combines them to create a broad composite. The bottom-up approach enables developers to explore problems or begin development without having a lot of information up front, and allows them to scale research and development efforts as needed. In our e-commerce example, you might start with the basic functions of adding items to the cart. Next, you would combine these functions to build larger components, such as the entire shopping cart module. And finally, you integrate these larger components to form the complete system and ensure that all the parts work together seamlessly. Let's bring this all together by considering the example of GrooveEco, a rapidly growing e-commerce company offering sustainable living products. GrooveEco's dev team has observed that their recently unveiled product recommendation engine has been plagued by low reliability. They apply logical thinking to work through this challenge, starting with these premises. Faulty algorithms cause errors, and errors lead to reliability issues. They then move on to conclude that the recommendation engine's low reliability is likely due to an error with an algorithm in the product's software. This helps them to identify a specific problem to focus on. They then break down this problem using a top-down approach, identifying the main recommendation algorithm as a potential culprit. They then decompose the algorithm into smaller functions for user behavior analysis and product matching. By individually addressing each smaller function, they are able to progressively hone in on and address the root cause, improving the overall recommendation system. In this video, you learned how to apply logical thinking in programming to help you solve problems efficiently and create robust solutions. By mastering deductive reasoning and problem decomposition, you can tackle any coding challenge problem systematically and effectively. Imagine you're faced with a puzzle, but this puzzle isn't static, it's evolving. As you start to piece it together, you realize that each step you take transforms the puzzle, revealing new challenges and opportunities. Logical thinking in programming works the same way. It's not just about finding where pieces fit together, it's about anticipating how the pieces interact to change the bigger picture as you progress. Let's dive deeper into how logical thinking can help you not only solve, but also adapt to the complex challenges of writing and debugging code. In this video, we'll connect logical thinking to practical programming tasks. Recall that logical thinking in programming refers to the process of applying systematic reasoning to define a problem and arrive at a solution. Within the context of programming, developers most frequently use two primary logical thinking skills, deductive reasoning and inductive reasoning. Now that we've established the connection between logical thinking and programming tasks, let's dive into real-world scenarios. By exploring these examples, you'll see how developers use logical thinking to tackle common challenges in their work. We'll start with a situation where you would use deductive reasoning to solve a common programming issue. Imagine you're debugging a function that is supposed to calculate the square of a number, but it is returning incorrect values. The best place to start would be to identify where the function is likely going wrong. And in this case, you could start with the general principle that the square of any number should be that number multiplied by itself. Based on this general principle, you can then apply deductive reasoning to hypothesize that the issue most likely lies with a specific operator within the function. Further investigation shows that instead of using a multiplication operator to multiply the number by itself, the function is incorrectly using an addition operator to add the number to itself. The final step would be to test your hypothesis by modifying the suspected part of the code with the correct operator and then thoroughly testing it with a variety of inputs to see whether the issue is resolved. By using deductive reasoning, we identified and resolved an issue in a function. But logical thinking isn't limited to fixing bugs. It's also vital in improving performance. Next, let's turn our attention to a scenario where inductive reasoning helps optimize an algorithm. Imagine that you're working to optimize an algorithm to speed up its execution. You could start by analyzing the algorithm's performance, and doing so reveals repeated instances when the algorithm slows down while analyzing large data sets. Next, you would apply inductive reasoning to focus on the specific causes of these drops in performance. On closer examination, you discover that each time the algorithm processes a new record, it rechecks all the previous data it already processed, which is a redundant and unnecessary step, thus causing a systematic drop in performance. Finally, you would refactor your code to optimize these operations. In this case, you would rewrite your code to eliminate the redundant checks and then test for improved performance. After optimizing an algorithm, the next logical step is ensuring that new features integrate smoothly into your codebase. Let's explore how logical thinking guides the design process and ensures seamless integration. Imagine you're adding a dark mode feature to an existing mobile app that already has a settings menu where users can change preferences. Your first step would be to clearly define requirements such as the design and placement of the settings UI, the workflow for selecting and toggling the settings, the color palette and icon selection, and so on. Next, you would use deductive reasoning to determine how the new feature will interact with existing components based on the general principles of your codebase. For instance, you know that in the current app, any setting that a user changes is saved into app settings file. Therefore, the new dark mode setting will need to be added to this file so that when a user selects it, the app can read this preference from the settings and apply it into the UI. Finally, you would implement and test the code for the new feature to ensure that it works as expected within the existing system. For instance, after updating the settings file and application logic and modifying the UI to support dark mode, you would test the apply theme function to ensure it toggles modes correctly, manually switching between light modes and dark modes to ensure that the UI updates as expected, and verify that saved theme preferences persist across app restarts. By applying logical thinking, you've successfully designed, implemented, and tested a new dark mode feature that integrates smoothly with your existing application. You've seen how using logical thinking in debugging, optimizing, and designing features helps break down complex problems into manageable parts. This systematic approach not only simplifies problem solving, but also enhances your ability to create efficient, reliable solutions. This approach leads to writing clearer, more efficient code, debugging more effectively, and ultimately building more reliable software. In this video, you learned how to connect logical thinking to practical programming tasks. As a programmer, you can practice logical thinking by consciously integrating inductive and deductive reasoning into your everyday programming tasks. Doing so will help you tackle any challenges as systematically and efficiently as possible.
Every programmer, regardless of experience, encounters moments of frustration when errors seem impossible to solve. Even the legendary Grace Hopper, a pioneer in computing, faced such challenges. In 1947, while working on the Harvard Mark II computer, Hopper and her team discovered a moth trapped in a relay, causing the system to malfunction, a discovery that led to the coining of the term debugging. This story is more than just a historical anecdote. It symbolizes the universal and timeless struggle of debugging, an essential skill that separates effective programmers from the rest. In this video, we will explain the basic principles of debugging. Debugging is the process of identifying and resolving errors or bugs in a computer program. The thing to remember is that no code is ever completely error-free. Errors are a natural part of programming, and even the most experienced developers encounter them regularly. Let's start by looking at the first type of error you might encounter: syntax errors. Recall that syntax errors are mistakes in the code that violate the rules of the programming language. Syntax errors occur when you write code that doesn't follow the syntax rule of the programming language. These are usually caught by the compiler or interpreter. Now that we've defined syntax errors, let's look at an example in C# where a syntax error could arise. Suppose you have a method called start, and let's suppose you have a string called welcome message with an initial value of welcome to my web application. But you've forgotten to close the string properly by failing to add the final quotes in the string. When you try to compile this code, the compiler will give you an error similar to this: error CS1002, semicolon expected, error CS1513, bracket expected. This is because the compiler was expecting the initial quotes to be closed by writing the closing quotes and the closing brackets too. The compiler will be confused, and thus the code needs to be debugged. Fortunately, syntax errors are among the least of your concerns, as they typically are caught by the compiler. Modern code editors also often provide suggestions on how to fix them. Visual Studio Code will even provide a line number where the syntax error was found and put a red line under the code it thinks caused the error, even before you try to compile the code. Additionally, most editors now use color coding, which helps you spot errors visually. Something will often look off when there's a mistake. With time and practice, you'll start recognizing these errors even before you hit compile. Now that we've covered syntax errors, let's move on to runtime errors, which require a bit more knowledge and expertise to handle. Unlike syntax errors, which occur during the compilation phase, runtime errors occur during the program's execution. They often cause the program to crash or behave unexpectedly. Runtime errors happen when the program runs and it encounters an operation it cannot handle. These are typically caused by invalid operations or memory issues. To illustrate this, let's consider an example where a division operation can lead to a runtime error if not properly handled. Here we have a method called divide numbers that receives two parameters, the numerator and the denominator. The issue arises because the programmer has to use a basic division operation. If the code attempts to divide two numbers without proper error handling, a user might try to divide by 0, which, as we know, is impossible, and this will result in an error. This type of error is usually managed by the runtime environment such as the .NET framework. However, these environments aren't always effective at handling these errors. They often cause the program to crash abruptly. So while runtime errors can be frustrating, they're usually obvious because the program fails, alerting you to the issue. The real challenge lies in the logical errors, those hidden mistakes that don't cause a crash, but silently produce incorrect results. Let's examine logical errors. Recall that these are mistakes in the program's logic that produces incorrect results but do not crash the program. Logical errors are often the hardest to spot because the code's syntax is correct. So the compiler compiles, nothing crashes, and the code appears to work, but it produces incorrect results. Let's look at an example. Here we have a method called applied discount. It has two parameters, the price and the discount percentage. Suppose we make a logical error by incorrectly applying a discount percentage using subtraction instead of multiplication. The code will compile without syntax errors, and it will not produce any runtime errors. However, it is incorrect because it doesn't produce the right results. Invoking this method with $1,000 and a 50% discount should give you $850. But since the programmer wrongly used a formula with a subtraction, it will give $985, which is an error. Now that we've identified the different types of errors, let's explore how to diagnose and fix them with debugging techniques. The first tool in your debugging toolkit is breakpoints. Recall that breakpoints allow you to pause the execution of your code at specific points so you can inspect the state of the program. Setting breakpoints in your code can help you pause execution at critical points and examine variable values and program flow at different stages of your program. To use breakpoints in an IDE like Visual Studio Code, you set them in the line where you think something is happening or where you want to inspect what is happening more deeply. Remember that breakpoints do not work for syntax errors since they stop or break the execution when the program is running. Thus, breakpoints work for runtime and logical errors. After setting your breakpoints and pausing your code at critical points, the next step is to inspect the values of your variables. Inspecting variable values allows you to check the current values of variables at different points in your code. Once you've checked the values of the variables, you can step through the code. Stepping through your code allows you to execute your program one line at a time to closely observe its behavior. Stepping through your code line by line helps you understand how the program flows and where it might go wrong. But sometimes you need the code to run and print messages allowing you to examine their content. The classical way to do this is by printing error messages to the output so you can analyze them. Have you ever encountered an error in an app where the window comes up and tells you, oops, something failed, with a bunch of technical information that users often do not understand? Well, that's there because a programmer included a message printing of some sort. The most basic way to do this is to insert console.writeLine statements to print in a console. This can be useful if you want to inspect many variables simultaneously or just see the code flow in a single printing. Reading and understanding error messages can tell you where and why your code fails. When printing messages, pay close attention to the line numbers and descriptions in error messages to quickly locate and fix issues in your code. While traditional methods like reading error messages are valuable, there's an even more practical approach available in modern IDEs, the debugger's inspector. In this video, we have explored the basic principles of debugging. By understanding common types of errors, such as syntax, runtime, and logical, you can better anticipate and address the issues that arise in your code. As you continue to practice and apply these techniques, you'll gain the confidence and skills needed to tackle any coding challenge that comes your way. Debugging is a valuable skill for every developer, ensuring that your code runs smoothly and efficiently. Mistakes in code are inevitable, but knowing how to identify and fix them can save time and prevent potential issues. In this video, we will learn to apply debugging techniques to identify and fix errors in code. Let's explore some tools that can aid your debugging efforts. One of the go-to tools for many developers is Visual Studio Code. Here's a common scenario: a simple piece of code that divides two numbers. Everything seems correct on the compiler. Variable names are clear and commas and semicolons are in the right places. As a result, the compiler doesn't flag any syntax errors, meaning there's nothing wrong with the code structure or formatting. However, if this code runs and the user passes 0 as the denominator argument, a runtime error will occur. You will find a runtime error only when the program executes. The error would occur in this case because having a 0 in the denominator is a mathematical impossibility. To fix this, many programmers use a debugger. A debugger is a tool that helps developers find and fix errors or bugs in their code. It allows you to run your code step by step, inspect variables, and understand the flow of execution to identify where things go wrong. One of the most popular debuggers front-end developers use is integrated into Visual Studio Code, VS Code, and you can access it through the debugger button in the top right corner. In the VS Code debugger, you can set breakpoints to stop the program's execution, watch variables, and step through your code to understand exactly how it runs. This makes VS Code a powerful tool for quickly identifying and fixing errors, which improves your code's quality and reliability. Let's find out how this works in our example where we're dividing two numbers. We built our divide numbers method. It gets two parameters and returns their quotient. In this example, we'll execute this code and call the method with a 0 in the denominator. To do this, I store the result in a variable called result. Here we are dividing the numerator 10 with the denominator 0, and then we print the result. The code compiles, so there aren't any syntax errors. But when I run the program, it shows the result is and then an infinite sign. This is a runtime error. When faced with an error like this, you can count on several debugger features to help you debug the code. The first one is breakpoints. Here's the code for the divide numbers method. In VS Code, you can set breakpoints by clicking in the gutter next to the line number where you want to pause the execution. We can add a breakpoint in this line. The next time the program runs this line, it will stop before executing, so you can determine what may be happening before this breakpoint. In general, you want to add breakpoints on the lines where your variables change so you can inspect their values later and review whether they are as expected. After setting your breakpoints, the next step is inspecting your variables. This is where you can determine exactly what's happening in your code at that precise moment when the breakpoint is hit. Checking the values of variables during execution helps you verify that your program is manipulating data as expected. The debugger includes a tool called the inspector. You can use it to hover over a variable to reveal what value it's holding. In this case, the denominator has a 0. Once you have checked the variables, you can manually move to the following line using the Step Through Code feature in the debugger. This lets you move through the code line by line using the toolbar controls to follow exactly how things are flowing and to catch where things might be going wrong. The debugger toolbar shows a set of buttons that you can use. The first button is Continue, which resumes program execution until the next breakpoint is hit or the program ends. The next button is Step Over, which executes the current line of code and moves to the next line, but does not enter into functions or method called by that line. Then the Step Into button. This executes the current line of code and, if the line contains a function or method, enters into that function to allow line-by-line debugging inside it. Next, the Step Out button, which completes the execution of the current function and returns to the calling function, then pauses. Then the Restart button, which stops the current debugging session and starts it again from the beginning. Finally, the stop button ends the current debugging session entirely, halting all code execution. Stepping through code works once the debugger has stopped the execution as mandated by a breakpoint. In this example, I've added a variable called result because I want to inspect the result of the operation. To do so, I've added a breakpoint in this line. At this point, you can inspect the variables and check what is happening inside your code. If you want, you can step through it to find out exactly where the error occurs. In this case, we notice the variable result has a 0, which would cause the error we're investigating. Stepping through the code allows you to pinpoint exactly where issues occur. For example, when I step over this line and inspect the variable now, I get the odd result of having a value of infinity, which was the unexpected behavior to begin with. With the right focus, you can locate the errors in your code. Using the debugger's inspector will help you understand the values of variables to get more information on them. In this video, we explore the importance of debugging techniques to efficiently identify and fix errors in your code. We've used the Visual Studio Code Debugger, which allows you to set breakpoints, inspect variables, and step through your code, providing a powerful way to understand and resolve issues. By mastering these tools and techniques, you'll enhance your problem-solving abilities and become a more confident, efficient programmer. When learning a new programming language, getting the structure and syntax right from the beginning can be the difference between smooth progress and countless hours of troubleshooting. When starting with C#, understanding how each part of the program fits together is essential to writing clean, functional code. Mastering these basics now will set the foundation for everything you build moving forward. In this video, we will explain the fundamental syntax and structure of C# programs. We'll cover key concepts such as classes, variables, control structures, and methods. We'll also explore some simple code examples to illustrate these concepts. First, let's examine the structure of a basic C# program. C# programs start with a class definition and contain methods where the actual logic resides. This C# code block defines the program class, which contains all the executable code. The static void main method serves as the entry point for the program. The braces define the blocks of code for the class and method. The console.writeLine command outputs the text "Hello World" to the console. This is the program's body where the work is done. Next, we'll examine variables, which are used to store data that can be used and manipulated within the program. Variables need to be declared with a type keyword that tells the program what kind of data the variable holds. There is an exception which we'll examine shortly. This sample code declares 4 different variables and initializes them with a value. First, int age equals 25 declares an integer variable called age and assigns it the value 25. Integer data types can only hold data that are whole numbers. The second variable, name, we declare with the string data type. We also assign the text John to the name variable. String variables can only hold text data. Our final 2 variables use a special type keyword, var. These variables don't declare a type up front. Rather, C# determines what type of value the variable holds when the program runs. In this example, we have one variable count that is initialized with the integer 10, and another variable message that is initialized with the string value hello. Both are declared with the type keyword var. Now let's examine how to create control structures in C#. Control structures manage the flow of the program. The most common control structures are if statements and loops. These structures help the program make decisions and repeat actions. We'll start with the if-else statement, which evaluates true-false conditions. In this sample code, the statement if age is greater than or equal to 18 checks whether age is greater than or equal to 18. Notice that we use the greater than and equal signs together to check whether the age is 18 or greater, and not just greater than 18. If that statement is true, the program prints, "You're an adult." If that statement is false, the program moves to the code in the else section of the code and prints, "You're a minor." This structure allows the program to take different actions based on the condition. The next type of control structure is the loop, which you can use to run the same block of code repeatedly. Let's examine how loops work in C#. In C#, a for loop is defined with the for keyword. The code you want to run repeatedly is put between the curly braces. Then we define the conditions for the loop in the parentheses after the declaration keyword. In this code sample, we first initialize the iterator, I, to 0. This sets the starting value of the loop. Then we set the condition for when the loop will exit. Here we tell the loop to run only as long as I is less than 5. Finally, we use the code I++ to add 1 to the variable I each time through the loop. Inside the loop, we write the code console.writeLine I, which prints the value of I to the console. This sample will print the numbers 0 to 4 to the console. Methods are the final concept we'll examine. Methods are functions that exist and work in classes in an object-oriented language like C#. They are blocks of code that perform specific tasks. They can take parameters and return values. This helps organize the code and make it reusable. Let's investigate how they work and how they're constructed. In this code sample, we create a class called Calculator. We can add code to this class that can perform all the operations of a calculator. By adding that functionality to a class, we group code that does similar work into one place and give it the ability to work together. The class has two member variables called number1 and number2 that have the int data type. These are declared as private since they'll only be used by the methods in the class. For this example, we'll add one method to the class called add, which is declared as an int. Declaring the method this way means that the value the method returns to the code that called it has to be an int data type. Because we're adding numbers, we implemented two integer parameters. These are the data that will pass into the method. Now we'll assign the member variables to the value of the input parameters in the add method. Because the member variables were declared as a part of the class, the method can use them to do its work. This is one of the differences between a method and a function. A method can use members of the class and a function cannot. Finally, the body of the method sums the values of the parameters number1 and number2 and returns the result. This method operates similarly to a function by processing data and returning a result. But you'll notice that it works inside a class and can interact with and operate on other class members. Now let's bring all these concepts together by building on our calculator program. We'll use a similar class and method from the previous example and declare the calculator class that includes the add method. Next, we'll add a second static method called main. We'll declare main with a void return value since this method doesn't take input parameters or return a value. Now we'll add two member variables, num1 and num2, declared as the type integer. We'll initialize num1 with the value 5 and num2 with the value 10. Next, we declare a variable called result with the type int. We'll set its value to the result of the add method. We pass in the values of num1 and num2 as parameters for the add method. Finally, we use console.writeLine to print the value of the result variable to the console. In this example, the result will be 15, so the console will show the sum is 15. We've now covered the basic syntax and structure of C# programs. We examined the structure of a program, explored variables and data types, examined control structures, and discussed methods. We also created a simple calculator program to tie everything together. These building blocks are essential for writing more complex C# applications.
Writing and executing code is one of the most effective ways to understand programming. In this lesson, you'll see how C# comes together as we dive into creating simple programs. We'll cover the essential steps to write and run your own C# code, giving you a solid foundation to build on as you continue your journey into the world of programming. Let's get started and see how these concepts come to life in practice. In this video, we will write and execute simple C# programs. We will write and run simple C# programs to apply the concepts we've learned. These programs include a basic calculator, a loop to display numbers, and a method to process user input. Let's start with something straightforward, a basic calculator. We'll use this program to perform simple arithmetic operations like addition and subtraction. Ready? Let's get started. To get started, we'll need to define a class called calculator. This is where we'll house the methods for performing addition and subtraction. Let's go ahead and set that up. For this, we'll start by creating a class with public class calculator and adding the brackets, which will include methods for addition and subtraction. Now that our class is set, the next step is to declare some variables. These will hold the numbers we're going to work with. Let's add those in now. For now, our calculator will operate on two numbers, so we will define them as this. Int, as they will be integers. Just to make it simpler, we used number 1 for the variable name. The system will initialize it automatically at 0. We do the same for the second variable, called number 2. With our variables in place, it's time to write a method that does the actual math. We'll create a method that takes two numbers as inputs and returns their sum. For this, we've created a method called add that sums number 1 and number 2 and returns the result. Now that we've got our method ready, it's time to see it in action. To do that, we'll need to write the main method inside our calculator class. This is where it all comes together. Let's take a look at how it works. We've written the main method, which remember is the starting point of the program. This method is quite simple. In this method, I assign 5 to the number 1 variable and 10 to the number 2 variable. Then I created a variable called result to store the return of the add method. And I called the method immediately by saying add and these parentheses. Then I went ahead and used this statement, console.writeLine, passing the concatenation of sum and the result from the add method. We would expect it to show 15 as the result. If you run this code, it should write something like this in the terminal, sum:15, which is the expected result. Now try adding other pairs of numbers and see if the result is what you'd expect. You can also try to create a subtraction method in the same fashion. Let's pause for a moment to discuss the static keyword we've been using in our variables and methods. The static keyword allows a variable or method to be accessible throughout the program without needing to create an instance of the class. We'll continue using static for now since we haven't covered objects yet, but keep in mind that it's a useful tool for keeping your code straightforward and accessible. Let's move on to something a bit different. Our next task is to write a program that displays numbers from 1 to 10 using a loop. Think of it like setting up a countdown timer or listing the steps in a process. You repeat similar actions over and over until you reach the end. This will show us how to control the flow of our program. Let's get started. Again, start by defining a class named numberDisplay. Next, write the loop method to display the number. In this case, we're using a for control structure. I've created an index that initializes with an int I that starts at 1, and it iterates while I is less than or equal to 10. It always increments by 1 on each step, noted by the ++. And on the for's body, we just print the index number with this console.writeLine. As in the previous example, we will define a main method as the starting point of our program. Write the main method to call the display numbers method. And just a quick detail before we move on. As you may have noticed, the main method does not return int, but the word void. Void is a data type in C# that just means nothing. It is used when the method does not return anything. When you run this program, you will get a list of numbers from 1 to 10. Try to change the number of times the display numbers method iterates to see what happens next. The result should show you a list of numbers from 1 to the number of times you chose. So far, we've been running programs without any input from users. They just run as written with no changes to the variables. But imagine creating a survey or a game where users enter their choices. That's where handling user inputs becomes crucial. It's one of the most important parts of programming because it allows your program to interact with people in real time. Let's explore how we can make that happen. Start by defining a class named userInput. I've written a method called greetUser that starts by asking a user to enter your name using a console.writeLine. Next, we are declaring a variable with the string data type that can hold strings of characters, such as a name. Then we use the method console.readLine, which detects characters in the terminal until the user hits the enter key. The program then greets you by saying hello and then your name. As usual, we write a main method to call the greetUser method. When you run this program, it will ask you for your name and greet you. Let's say I type my name here and hit enter, and then the program will greet me. Hello, computer. Nice to meet you. In this video, we have written and executed simple C# programs, allowing you to apply the concepts we've covered so far, from creating a basic calculator and displaying numbers with a loop to handling user input. These exercises have provided a hands-on approach to understanding C# syntax and structure. As you continue practicing, you'll find that writing and running your own code becomes increasingly intuitive, laying a solid foundation for more advanced programming tasks. Keep experimenting with these examples, and soon you'll be able to build more complex and dynamic C# applications with confidence.
In this first step, we will create a simple calculator program that performs basic arithmetic operations such as addition and subtraction. We will start by defining a class and writing a method to add two numbers. In C#, a class is like a container for your program's code. It holds methods, which are sets of instructions that tell the program what to do. Think of a method like a recipe that the program follows step by step. Here we're going to add a method called add, which will add two numbers together. The word static means the method belongs to the class itself, and public means it can be accessed from other parts of the program. A variable is like a container that holds data that your program can use. Here we have two variables called number1 and number2 that will store the numbers we want to add. The method will return the result using the return keyword, which means the method sends the answer back to the part of code that called it. Now that we've created the add method, it's time to see how it works. To execute a C# program, we need to write a main method, which is the entry point of the program. This is where everything comes together. In C#, every program starts by running the main method, which is like the starting point of the program. When you run a C# program, the code inside main is the first to execute. In this case, inside main, we're going to assign values to number1 and number2, call the add method to calculate the sum, and use console.writeLine to print the results on the screen. Calling a method means running the code inside the method and using its result. Next, we will write a program that uses a loop to display numbers from 1 to 10. Loops are control structures that allow you to repeat actions multiple times. A for loop is used when we know how many times we want to repeat a block of code. In this case, we want to print numbers from 1 to 10. The loop has three parts. Initialization, int I equals 1. This sets the starting point for the loop. We start with I equals 1. Condition, I is less than or equal to 10. This tells the loop when to stop. As long as I is less than or equal to 10, the loop will run. When I becomes 11, the loop will stop. Increment, I++. This increases the value of I by 1 after each loop iteration, so the next number is printed. Now let's write a program that interacts with the user. This program will prompt the user for their name and greet them. Handling user input is important for creating interactive programs. In this step, we'll interact with the user by asking for their name. To capture the user's input, we use console.readLine. This waits for the user to type something and then stores that input as a string, which is a sequence of characters like a word or sentence. We store the user's input in a variable called name. Once we have the user's name stored in name, we can use console.writeLine to display a personalized greeting. Notice that we first prompt the user to enter their name with console.writeLine. After the user types their name, it is stored in the name variable using console.readLine. We then use that variable to greet the user by name, showing how input can be used dynamically. Console.readLine is useful for capturing input, while console.writeLine is used to display messages to the user. We will create a small console application that allows users to manage a simple to-do list. The program will let users add tasks, view the list of tasks, and mark tasks as completed. This will involve collecting user input, storing the data in an array, and using loops to interact with the list. When building a program, it's helpful to break it down into smaller tasks, which makes it easier to write and understand. In this program, we will add tasks to a list, view tasks to see what's on the list, mark tasks as completed when they're finished. To do this, we will use methods, loops, and arrays. Each part of the program will have its own task to perform, making it easier to work with. Arrays are useful because they allow us to store multiple tasks, and loops allow us to repeatedly check what the user wants to do next. Finally, we'll use debugging techniques to catch and fix any mistakes we might make. First, we need a place to store the tasks. We will use an array, which is a special type of variable that can store multiple pieces of data. Arrays are useful when we want to store several things of the same type. In C#, an array is like a container that holds several values of the same type. In our case, the array will hold strings, which are pieces of text representing the tasks. Arrays have a fixed size, in this case 10 tasks, which means we can only store up to the 10 tasks in the array. Each task will be stored in a separate spot called an index. We access each task in the array using an index which starts counting from 0. We'll also need a counter variable called task count to keep track of how many tasks are in the list. This variable starts at 0 because the list is empty at first. Each time a task is added, task count will be increased by 1, making sure the next task is stored in the next available spot in the array. Next, we will create a method to let the user add tasks to the list. When the user types in a new task, we will store it in the array at the correct position using the task count variable. We'll use a method called addTask to ask the user to enter a task. The method will store this task in the array using console.readLine, which captures what the user types. The task will be saved in the next available spot in the array, which is determined by task count. Remember, arrays start at index 0, so the first task will be stored in tasks 0, the second in tasks 1, and so on. After each task is added, we increase task count by 1 to make sure the next task goes into the next available spot. This ensures that every new task is added to the right spot and we don't overwrite any existing tasks. The task count variable helps us keep track of how many tasks have been added and where the next one should go. Now we will create a method to display all the tasks the user has added so far. This method will loop through the tasks array and print each task. To view the tasks, we'll use a loop to go through each element in the tasks array. The loop will start at index 0, the beginning of the array, and will stop once it reaches task count. This ensures that we only print the tasks that have been added and avoid printing empty spots in the array. Each task will be printed with a number starting from 1 for easier reading, even though array indices start from 0. The number I plus 1 is used to make this more user-friendly. Now we'll create a method to let the user mark a task as completed. This will allow the user to update a task in the array and show it has been finished. The user will choose a task to mark as completed by entering the task's number. Arrays in C# start counting from 0, but the user will enter a number starting from 1. So we need to subtract 1 from their input to get the correct index in the array. For example, if the user selects task 1, we need to update tasks 0. Once we find the correct task in the array, we will modify it by adding the text completed to show it is finished. This will update the task and make it clear to the user that it has been marked as complete. Finally, we will write the main method that brings everything together. This method will let the user decide whether to add a task, view tasks, or mark a task as completed. We'll use a while loop to keep the program running until the user decides to quit. Inside the loop, the program will show a menu of options. The user can select an option to add a task, view task, or mark a task as complete. We'll use a switch statement to handle the user's input, calling the right method based on their choice. The loop will continue until the user selects the option to exit the program. In this step, we will introduce a common error that can happen in your program and walk through the process of finding and fixing it. Debugging is an important skill, and learning how to identify and solve problems in your code will make you a better programmer. Let's say the user tries to mark a task as completed, but they enter a number that is outside the range of the task list. For example, they enter 12, but there are only 3 tasks. This will cause an index out of range error because the program tries to access a part of the array that doesn't exist. Let's explore how we can debug and fix this problem. An index out of range error occurs when your program tries to access a position in an array that doesn't exist. For example, if your array has 3 tasks and the user tries to mark task 4 as complete, the program will crash because there is no task at that position. To prevent this, we can use error checking to make sure the user's input is within the correct range. To fix this error, we'll print the value of task number before accessing the array to check if it's correct. Then we will update the code to give the user an error message if they enter a number outside the range of the tasks. Once you've added the debugging line and handled the error, your program no longer should crash when the users enter an invalid task number. Instead, it should display an error message like, "Invalid task number, please try again."
As you have discovered, mastering programming fundamentals is crucial for developing effective code. To strengthen your foundational understanding, we began by reviewing fundamental programming concepts, including variables, data types, control structures, loops, methods, and pseudocode. Then, we combined logical thinking with core programming principles to help sharpen your problem-solving skills. Next, we covered fundamental debugging techniques and tools to help you detect and resolve errors in your code. Then we practiced building straightforward programs in C# using your foundational knowledge to create functional code. And finally, we worked on a project that combined all the concepts and debugging techniques, providing hands-on experience in applying your skills to a full development task. Mastering programming fundamentals is essential to creating reliable and efficient code. By honing these skills from understanding core concepts to debugging and building C# programs, you'll enhance your ability to tackle complex development tasks and deliver high-quality applications.
Welcome to Mastering Object-Oriented Programming in C#. This module covers the core concepts of objects, classes, inheritance, and polymorphism, and demonstrates how to apply them in C#. You'll also learn key design patterns and practices, implementing them strengthening your programming skills. We will begin by defining objects and classes and understanding their role as the foundation of object-oriented programming. You'll learn how these elements create a structured, reusable code base. Next, we'll examine inheritance and polymorphism, exploring how they allow flexibility and scalability in your applications. We'll break down their functions and importance in OOP. Then we'll apply these concepts in C# with practical examples, helping you see how they work in real-world scenarios. You'll gain hands-on experience to deepen your knowledge. After that, we'll explore common design patterns in OOP and identify how they provide solutions to recurring development challenges. You'll learn when and how to apply these patterns effectively. Finally, we'll implement classes and objects in C# through guided exercises, reinforcing your skills and confidence in applying OOP techniques. By the end of this module, you'll have the knowledge and practical skills to apply object-oriented programming principles in C# confidently. Let's get started with mastering object-oriented programming in C#. One of the disciplines in biology is classification. Scientists use specific properties to group animals to create classes like zebras, pelicans, and humans. Within these classes are individual zebras, pelicans, and humans that share properties of other members of the class, like stripes, beaks, and opposable thumbs. Classification helps scientists manage their research, understand how animals are similar and different, and even know what to expect from their behavior. Computer scientists have applied many of these concepts in a programming model called Object-Oriented Programming, or OOP. In this video, we will explain the basic concepts of objects and classes in OOP. Objects and classes are the fundamental coding building blocks of object-oriented programming. Code-based classes and objects are related in the same way that an animal is related to the class in which it belongs. Think of an object as an individual thing or an instance of a class, like a particular zebra. The class is a type of definition. It describes all the properties and abilities that the average zebra has. Let's explore these concepts in more detail, starting with the definition of a class. A class is a blueprint or template that defines a set of shared characteristics and behaviors for a group of things. Code classes are similar to classes in biology or botany in that they define the properties of the individual code objects and what they can do. Classes in object-oriented programming by themselves can't do much work. A programmer can't process data, interact with the user, or send API calls. But a class provides a blueprint for how to do all these things. Specifically, a class has three main features that define them. The first feature developers define in classes are properties. These are the individual items of data that an object stores or sets. For example, an authentication class may define properties like username and password. Classes also define methods, which are also referred to as behaviors or functions. Methods are the behaviors the class can perform. For example, the login class may define methods like validate, which checks the user's credentials, and login, which gives the user access to the system. Finally, through a feature called inheritance, classes can be extended to create subclasses that inherit properties and behaviors from the parent class, just like offspring in biology. This feature enables the developer to reuse and better organize code. For example, a developer may inherit the login class, reusing its properties and methods, but adding a new attribute called displayName that they can show on a user interface after the user has logged in. Because classes are definitions only, in order for them to do work, developers have to create a working version of them. This is called instantiation, and the process creates individual objects or instances of the class. An object is a distinct thing that possesses unique properties and behaviors that define its characteristics and actions. Code objects, like other types of objects, are defined by their properties and the things they can do within a program. Code objects have all the properties and methods of the class of which they are an instance. The object's properties are the data elements associated with the object defined by variables within the class. Its methods are the operations or functions the object can perform, defined by the methods in the class. Objects also have a couple of other features that differentiate them from the parent classes. Each object has a unique identity within the program, often represented by its memory address or a unique identifier. Because objects are instances of classes, the developer can create as many as they need, and each one is uniquely identified in the application. The object's state is determined by the current values of its properties. For example, a login object's state might include the values it currently holds for username and displayName. An object can only do what is defined in its parent class unless a developer uses inheritance to extend the class. Then an object created with an inherited class will have all the new properties and methods, as well as the original one from the parent. Now let's bring these ideas together using an example of a book class that might be used in a library system. The book class might have properties like title, author, and ISBN. It might also have methods like borrow and return. By defining these properties and methods, we can create specific book objects, each representing a particular book in the library with its own title, author, and ISBN. When a book is borrowed, the borrow method can update the status of the book, demonstrating how properties and methods work together to manage the state and behavior of objects in OOP. Object-oriented programming is an efficient and powerful programming model. By defining classes and creating objects, developers can write code that's more easily maintainable and reusable. Just as you don't need to understand the inner workings of a post office to use its services, developers don't need to know the internal details of a class to interact with it. Developers use the principles of encapsulation and abstraction to simplify how their code is used. In this video, you'll learn how to explain the principles of encapsulation and abstraction in object-oriented programming, and how these protect the internal state of an object and simplify its use. Let's start with encapsulation. Encapsulation is the principle of bundling methods and data into a class and restricting access to some of the class's components. This is done by managing the interfaces through which the class's data can be accessed and modified. When developers apply this principle, they keep an object's internal state hidden from outside code, exposing only what is necessary. Let's examine more closely how developers use this principle to create classes. Encapsulation protects an object's internal state by managing access to its attributes and methods. Developers use access modifiers like private, protected, and public to manage what data and methods other code has access to and how data can be modified. For example, suppose a bank developed an application and the code has a bank account class that includes data and methods for managing data related to a customer's account. The balance attribute stores the customer's account balance data. The developer might provide a public getBalance method that lets other code read the attribute, but no method for writing to the attribute. Encapsulation allows developers to expose parts of the object to any of the application's code using public methods. They also can expose other parts only to parts of the app that inherit from the class using protected methods. These principles give the developer fine-tuned control on which parts of the class are exposed and how broadly. Suppose the bank account class has an interest rate attribute that stores the interest rate the bank currently applies to the account. The developer doesn't want the interest rate attribute exposed, so they create no method for accessing it. However, they do want people to be able to make deposits and withdrawals, and so they provide public methods that enable these activities. Encapsulation is a principle that focuses on managing the data and methods of the class. It helps developers protect parts of the class they want to keep secure and expose the part that the rest of the application can use. Another principle of object-oriented programming, abstraction, defines what methods a class should implement without providing specific implementation details. Let's explore that next. Abstraction is the principle of defining what an object does but not specifying how it does it. Developers achieve this by creating abstract classes and interfaces. When developers apply this principle, they define an object's essential features and behaviors, but enable developers to decide how methods within those objects are implemented. Let's examine more closely how developers use abstraction to create objects. Developers can apply the principle of abstraction in two primary ways. They can use an abstract class when they want to share a common code base with concrete methods, which are methods that include the implementation code. But they also can include abstract methods that just define the interface, but don't provide any implementation details. Developers can also create interfaces that do not include concrete methods. You can think of an interface like a contract that defines a set of methods that an inherited class must implement. Interfaces typically only include what methods an inherited class must implement, but not the implementation code. Suppose in the banking application, the development team creates an abstract class for handling deposits and withdrawals. This class defines an amount attribute and declares the abstract methods for deposit and withdrawal. The savings account functionality inherits from this abstract class and provides specific logic for how deposits and withdrawals should be handled. The checking account code does the same. Any other part of the app that interacts with these accounts knows that both savings and checking will have deposits and withdrawal methods, without needing to be concerned with their implementation details. Now let's look at how the principles of encapsulation and abstraction work together. Suppose a library creates software to manage its inventory. The software's programmers create a library class that encapsulates data about books and patrons. It hides the internal data structures using private attributes and provides public methods like addBook and borrowBook. This protects the integrity of the library's data while allowing controlled access. Additionally, it uses abstraction by defining an interface catalog that exposes methods like searchBook and list available books. Any class that inherits from catalog implements its methods, making the system easier to use and maintain. In this video, you learned how to explain the principles of encapsulation and abstraction in object-oriented programming, and how these protect the internal state of an object and simplify its use. Encapsulation protects the internal state of an object by bundling data and methods within a class. Abstraction helps developers create consistent, predictable yet flexible classes. Applying these principles, developers can write secure and maintainable code. Have you ever wished you could take something old and make it better without starting from scratch? Object-oriented programming addresses this through the concept of inheritance, which enables developers to reuse code, but modify it and extend it only as needed. In this video, we will describe the concept of inheritance in object-oriented programming. Let's begin with the definition of inheritance. Inheritance is a fundamental concept in object-oriented programming that enables developers to create new classes based on existing ones. Similar to an inheritance in biology, code inheritance enables classes to inherit features from other classes. It allows a new class, known as a derived class, to inherit attributes and methods from the existing class. This is called the superclass or base class. When a developer creates a derived class, they get the attributes and methods of the base class, but also can extend their class by adding their own attributes and methods. This allows the developer to reuse the code from the base class without having to reproduce it. They also can add more features to the class and even modify the original attributes and methods if they need to. The new and modified features are isolated to the derived class and don't impact the base class. The relationship between the derived class and the base class is similar to the relationship between a child and a parent. The child may have many similar features of the parent, such as skin color, nose shape, and height, but the child will develop unique characteristics such as hair color and personality. This relationship creates a hierarchy in code that fosters reuse. It also allows developers to organize and manage code more efficiently. Inheritance creates a tree-like structure between classes. For instance, a bird class can be a base class for eagle and parrot derived classes. Both eagle and parrot will inherit common attributes and methods from bird, like fly, but can also have their own unique properties. The eagle-derived class may include a hunt method, and the parrot-derived class could include a speak method. The additional methods do not become a part of the base class, but remain isolated to the derived classes. By using inheritance, developers can reuse existing code and extend it with additional functionality. This promotes code reuse and reduces redundancy. In this video, you learned to describe the concept of inheritance in object-oriented programming. Inheritance enables developers to inherit properties and methods from existing classes and create hierarchical relationships. By applying this concept to their applications, developers can write efficient and organized code by promoting reuse and extension of existing functionalities. Modern messaging applications are more advanced in how they handle files compared to their predecessors. For example, if you share a video file, your messaging app might automatically provide a play button for your friend or colleague to experience the video. If you upload photos, they may see a flipbook-style interface that allows them to scroll through all the images. The app uses a single interface for files, but it adapts to perform different actions depending on the type of file you upload. Object-oriented programming provides a similar concept for working with code. Polymorphism enables developers to create a single method that performs different tasks based on the object they're acting on. In this video, you'll learn how to explain the concept of polymorphism in object-oriented programming. Let's begin by defining polymorphism. Polymorphism enables developers to use a single method name to perform different tasks based on the type of object it's acting on. This means a method can behave differently depending on what it's being asked to do. Here's an example of using polymorphism with an object. Developers first create a derived class by extending a base class. Through inheritance, the derived class has the methods and attributes of the base class. At this point, they can then use the implementation of the methods in the base class or override one or more methods and implement their own version of them. They can also add methods and attributes to extend the functionality of the base class. Let's explore this further with a real-world example. Suppose a developer creates a base class called Coffee Maker that has methods called water and beans. First, they implement the water method so that the Coffee Maker object can hold water in a tank, and the beans method so that the Coffee Maker accepts grounds. The developer then creates two derived classes called Drip and Super Automatic that extend the Coffee Maker base class. The first derived class is the Drip class. The Drip derived class uses the methods exactly as they are in the base class, but adds an additional method called Vessel that describes where the coffee is stored after it's brewed. The second derived class is the superautomatic derived class. The superautomatic derived class inherits the water and beans methods. The derived class uses the water method exactly as it is in the base class because this version of the coffee maker also has a tank to hold water. However, the superautomatic can also grind beans, so the developer overrides the beans method to include this functionality. Next, overriding methods in derived classes enables developers to change only what they need in a derived class and use the other base class's functionality without modification. Let's examine overriding in more detail. Overriding is a technique in object-oriented programming where a derived class provides its own implementation of a method that is already defined in its base class. This technique allows developers to create more specific types of objects that define their own version of a method. By overriding a method, a developer can design derived classes that refine or completely replace the behavior of methods inherited from the base class. Overriding gives developers the ability to design derived class methods that are appropriate to their specific context while using existing code objects and features. This encourages code reuse, but not at the expense of flexibility. In this video, you learned how to explain the concept of polymorphism in object-oriented programming. Polymorphism gives developers the powerful ability to modify or extend methods in derived classes to perform different tasks based on the object they're acting on. Overriding a method lets derived classes provide their own versions of what a method can do. These object-oriented programming concepts help developers write flexible and reusable code. Imagine having a blueprint for a house that can be reused and modified to build different types of houses. Inheritance in programming works similarly using properties and methods from an already existing class. In this video, we will apply inheritance in C# programs. By using inheritance in C#, developers can create a new class that inherits properties and methods from an existing class. The existing class is called the base class, and the new class is called the derived class. To begin, C# developers define a base class by using an access modifier. These keywords determine whether other parts of the code can access the class. Declaring a class as public means its members are accessible from any other class. Private class members are only accessible within the class itself, and protected members are accessible within the class and by derived classes. After the access modifier, the developer uses the class keyword followed by the name of the class to finish the declaration. The base class contains common properties and methods that other classes can inherit. Properties hold data that the class will use internally to guide how it functions or data that the class will process. The methods define the work the class can perform. Finally, the base class has a constructor, which is the entry point for the class. It's like the front door of a house where you enter and declare who you are and why you're there. The constructor can take input parameters which the developer can use to set the initial values for the class's properties. Let's explore an example. Suppose a developer wants to create a class that manages maintenance information for a pool. They declare the class as public, and it has two properties, chlorine level and water level. The constructor takes these values as input parameters and assigns them to properties. This simple class has a method called poolInfo that writes out the values that were passed into the constructor. This class has all the elements of a base class and can be easily expanded with more properties and methods to make the class a lot more powerful. Developers can further extend what a class can do by creating a derived class. A derived class inherits all the properties and methods of the base class, and developers can extend it without impacting the original base class. Let's examine how this works. Derived classes are defined similarly to base classes in C# by using an access modifier and a name for the derived class. To create a derived class, the developer follows the name by a colon and includes the name of the base class in the declaration. The derived class inherits all the properties and methods of the base class. Developers also can add their own new properties and methods. They get all the advantages of the base class but can customize it for a particular scenario. For example, a developer can create a derived class for a spa from the pool base class. They declare the derived class with the public modifier and name of the class spa, which is derived from the pool base class. The derived class has the chlorine level and water level properties that the base class has, but the developer decides to add a new property called heat level since spas are heated. The constructor takes data for all three properties as input parameters and assigns them to the derived class's properties. This derived class uses the pool info method it inherited from the base class to display the spa's information on the screen. In conclusion, inheritance in C# is a powerful object-oriented tool that enables developers to reuse code and make it easier to maintain C# code. In this video, you learn to apply inheritance in C# programs. Inheritance in C# involves creating a base class and then deriving a derived class using inheritance. By using inheritance, developers build organized, reusable, and maintainable code in C#. Imagine a single tool that can transform into different instruments depending on the task at hand. That's the power of polymorphism in programming. In this video, we will apply polymorphism in C# programs. Let's begin by defining polymorphism. Polymorphism enables developers to use a single method name to perform different tasks based on the type of object it's acting on. Essentially, this means a method with the same name can do different work depending on what it's being asked to do. Next, let's explore a few ways that developers can apply polymorphism in C#. Developers use polymorphism in C# by creating a virtual method in a base class. This indicates that the method can be overridden. Method overriding allows a subclass to provide a specific implementation of a method that is defined in its base class. Let's explore an example. Suppose a developer wants to create a class that manages musical instruments. They declare the class as public and it has a virtual method called play declared as public virtual void play that writes the message playing an instrument to the console when it's called. This class has a single virtual method that can be overridden by a subclass. These base classes also contain concrete methods which can't be overridden. To override the play method, the developer creates a subclass called piano that is inherited from the base class instrument. They create the play method using the override keyword, which is declared as public override void play. The overridden method prints the message the piano is playing to the console. A class could be created for other instruments in the same way, and each class would have a play method. Virtual methods aren't the only way developers can use polymorphism in C#. Developers can also create interfaces that do not include the method's implementation. You might be wondering, what is an interface? Well, an interface is a contract that defines a set of methods that an inherited class must implement. Interfaces typically only include what methods an inherited class must implement, but not the implementation code. For example, a developer creates an interface for the musical instrument play using the declaration public interface iPlayable. The method includes an empty method called play, which a subclass can use to create a concrete method that does work. To implement this interface, the developer creates subclasses called guitar and piano that are inherited from the interface iPlayable. Then, they create the play method, which is declared as public void play. The method writes the message the guitar is playing for the guitar subclass, and the message the piano is playing for the piano subclass. The use of interfaces promotes the consistent use of methods across different classes. In closing, developers should use virtual methods in C# when designing base classes when they want to include implementation detail for the subclasses. Interfaces in C# are best for scenarios where developers want to provide a basic set of methods a subclass must implement without the need to provide detail on what those methods might include. Both are powerful ways to use polymorphism in C#. Polymorphism in C# programs. We explored how to apply polymorphism by overriding methods and using interfaces. Understanding polymorphism helps developers write flexible and reusable code in C#. We'll start by creating a base class called Animal and two derived classes, Dog and Cat. This will introduce you to the concept of inheritance, where Dog and Cat will inherit properties and methods from Animal. Inheritance allows you to create a general class, Animal, that can be used as a base for more specific classes, Dog and Cat. This helps us avoid repeating code because common properties and methods are defined in the base class. For example, all animals might make a sound, but each animal makes a different sound. In our program, the animal class will have a method called makeSound that each specific animal class can override to provide its own sound. When we want to allow a method in the base class to be overridden in a derived class, we use the virtual keyword. This tells C# that the method in the base class is meant to be overridden in any class that inherits from it. The derived classes, Dog and Cat, then use the override keyword to provide their own implementation of the makeSound method. This allows each derived class to customize the behavior of the method. Think of virtual as giving permission to change how something works in the base class, and override is actually making that change in the derived class. In this step, we will call the derived classes from our program class using the main method as the entry point into the application. In the main method, we instantiate a dog object and a cat object using the new keyword. Once objects are instantiated, we can call any public method on those objects that we've defined in the class. We then call the makeSound method in each object, which should print the associated output to the console. We don't need input parameters for the makeSound method since the output is defined in the derived classes themselves. Now we will introduce interfaces which allow us to define a contract that classes can implement. This is different from inheritance but can be used alongside it. An interface is like a contract that classes can agree to follow. It defines methods that must be implemented by any class that implements the interface. Unlike classes, interfaces do not provide any implementation details. They only define what methods must be provided. Interfaces are useful because they allow us to specify a set of methods that different classes must have, even if those classes are not related through inheritance. For example, if we have an interface iAnimal with the method eat, any class that implements iAnimal must provide an implementation for eat, ensuring that all animals have this method. Interfaces provide a way to guarantee that certain methods will exist on any class that implements them. In this step, we will use polymorphism to interact with objects of different classes through a common base type or interface. This allows us to call methods on different objects in a unified way. Polymorphism allows us to treat different objects as if they are instances of the same class or interface. This is powerful because it lets us write code that can work with any class that shares a common base class or interface. For example, we can create a list of animal objects which include instances of dog and cat. When we call makeSound on each object in the list, the correct version of the method is called for each specific object. This works because both dog and cat override the makeSound method from the animal base class. Polymorphism is like a universal tool that lets you interact with different objects in a standardized way, regardless of the specific type. This is particularly useful when you want to work with a group of objects that share a common interface or base class but behave differently. As software development has evolved, engineers continue to learn how to construct programs that are efficient, easier to maintain, and scalable. The common solutions that contribute to building software like this are called design patterns. Software engineers have created a set of patterns that all developers should follow. In this video, you will learn how to explain the importance of design patterns in object-oriented programming. Design patterns are reusable solutions to common problems that provide a standardized approach to architectural challenges in software design. They provide the developer with a template for how to solve an architectural problem when designing an application. Using a design pattern means following best practices. Because the pattern is common among developers, it helps improve how readable the code is, making maintenance easier. These patterns also make code run more efficiently. Let's explore a simple example. The singleton pattern is a design pattern that specifies that a class can have only one instance and should provide a single point of access to it that is available from anywhere in the application. This is useful for managing shared resources like a configuration manager or a database connection. Now that we've explored the singleton pattern, which helps manage the creation of objects efficiently, let's dive into other types of design patterns that address different challenges in software development. Creational patterns specify how developers should create objects in an application. The pattern focuses on writing code in a way that creates objects that are suitable to the situation in which they'll be used. For instance, even though creating global variables might be easier and less complex, overusing them could make an application less secure, consume more memory, and make code maintenance difficult. Creating a local variable that exists in a particular scenario and then is destroyed is a better pattern in general. Another category called structural patterns deals with how objects are composed and how classes and objects can be combined to form larger structures. Developers use these patterns to organize the relationships between objects and classes in a way that minimizes the impact of changes. One example of a structural pattern is the adapter pattern. Let's examine how this pattern works with an example. Suppose an object doesn't have an interface that is compatible with the interface of another object. Developers can use the adapter pattern to enable them to work together. If they later change the way one object works, they might only need to update the adapter, not the entire system. This minimizes impact to the system. For example, let's say you have an application with a square peg class and a round hole class. The round hole class expects objects to have a method for getting a radius, but the square peg class has a method for getting its width instead. The adapter pattern can help you write an interface so that these two objects work together. Now let's examine the final category of development patterns that focuses on how objects interact. Behavioral patterns focus on defining the rules and methods for how objects and classes operate together. They establish clear protocols for how tasks are divided among different parts of the program and how data flows between them. When developers effectively apply behavioral patterns, different components of the system will work together more efficiently, even as the system grows or changes. These three categories describe design patterns that developers should follow when creating software that's easier to maintain and that runs more efficiently. But developers might ignore patterns, so engineers have created tools to help software developers follow and enforce design patterns. Modern software development tools like Visual Studio Code are equipped with extensions that assist developers in writing code that aligns with established design patterns. For example, some extensions can analyze your code as you write and suggest refactorings that align with common patterns, such as converting repetitive code blocks into reusable functions or classes. Visual Studio Code's integrated development environment can analyze code and detect deviations from best practices, including the improper use of patterns. When they detect a deviation, they can alert the developer so they can make changes. These tools help developers write code that is consistent and adheres to the architectural patterns. Using a combination of tools and practices, developers should continually work towards writing software that adheres to accepted design patterns. This will make code easier to maintain and will help them create powerful systems that can more easily grow and evolve. In this video, you learned how to explain the importance of design patterns in object-oriented programming, including creational, structural, and behavioral patterns. By applying these patterns, you can write efficient, maintainable, and scalable code. Imagine working on a complex project where you constantly face the same challenges. Over time, you develop smart, repeatable solutions that make your work easier and more efficient. In software development, we call these repeatable solutions design patterns. They are tried and tested ways to structure your code, making it more efficient and scalable. In this video, you will learn to recognize and describe common design patterns. Design patterns are like reusable solutions for common problems in software design. They give you a standard way to tackle architectural challenges, making your code more reliable and easier to maintain. There are many design patterns that developers use to design their software. We'll explore a few of the most common. First, let's discuss singleton pattern, which ensures that a class has only one instance throughout your application and provides a single point of access to that instance from anywhere in your code. Developers use the singleton pattern to manage shared resources. For example, a database class can implement the singleton pattern to ensure there is only one connection to the database throughout the application. To implement this in C#, a developer creates a public class called database. They create a private variable that holds the instance of the database object, and a private constructor that writes database connection established to the console when it's called. The developer then creates a public method called getInstance that assigns the private variable to a new instance of the database object and returns that instance to the code that called it. But before it assigns the object to the private variable, it checks first to see if it's already populated. If it is, it uses the instance that already exists. This enforces the pattern that there is always only one instance of the database object in the program. The access modifier of the database constructor is private, which prevents any external class from creating a new instance of the database object. This is key to enforcing the singleton pattern. Now that we've explored the singleton pattern's role in managing a single instance across an application, let's look at another essential pattern, the factory pattern. This pattern not only helps in creating objects, but also ensures that your code remains stable and adaptable even as changes are made. Let's investigate how this factory pattern works. In the factory pattern, instead of creating an object directly, your code asks a special method or class called a factory to handle the creation for you. This way, your code doesn't need to worry about the details. The factory takes care of it, making your program more flexible and easier to manage. The factory receives some inputs, such as a parameter, that tells it what kind of object it needs. The factory then decides which specific type of object to create based on that input. By using the factory to create objects, the pattern keeps the code that requests an object separate from the code that actually makes it. This separation makes it easier to change or add new types of objects later on without affecting the code that uses them. To implement the factory pattern in C# for a notification system, you start by creating a public interface called iNotification. This interface will include a method called send, which takes a message as a parameter. Then you move on to the next step, creating two derived classes that inherit from the iNotification interface. One derived class will handle email notifications and the other will manage SMS notifications. Each of these derived classes implements the send method, which outputs the notification to the console. Finally, the developer creates a new class called Notification Factory that handles creating the email notification and SMS notification objects. They implement a method called createNotification that uses the iNotification interface as its type. This method also takes an input parameter called channel that tells the factory which type of notification object to create. Using this pattern, the developer can modify how the email and SMS notification objects are designed without impacting the code that requests them. The code that requires these objects just calls the createNotification method, passing in the channel parameter, and the factory handles the rest. Finally, let's explore the observer pattern, a key behavioral pattern that is crucial for managing communication between objects in complex systems. Imagine you're developing a user interface that needs to update in real time whenever the underlying data changes. This is where the observer pattern shines. It enables your system to respond dynamically to changes, keeping everything in sync without manual intervention. The observer pattern enables one object to automatically notify and update multiple other objects when its state changes. This pattern is particularly useful in systems where different parts must respond to changes, such as updating a user interface when data changes. Let's learn how a developer might implement this pattern in C# for a weather station application. To implement the observer pattern, you start with creating a public interface called iObserver. This interface includes a single method named update, which accepts a temperature parameter. This step lays the foundation for how observers will receive updates. The next step is to create the weather station class, which acts as the subject. This class manages a list of iObserver instances and is responsible for notifying all registered observers whenever there's a change in its internal state, like a temperature update. It has a private list member called observers that can hold iObserver interface objects. It also has a private member called temperature that holds temperature values. The developer creates methods for adding and removing objects from the observers list, as well as a method called notify observer, which iterates through each object in the observers list and then calls the update method on each one from the observer interface. This method passes the values set in the temperature member to the update method. The temperature member is set in the final method in this class called setTemperature. This method includes an input parameter called newTemperature, and the method sets the private temperature member variable to its value. It then calls the notifyObserver method. The developer then creates a concrete public derived class called phoneDisplay. The class will notify a phone interface of any changes in the temperature. The developer can use an app or a tool built into the phone to listen for this message. The developer also creates a concrete public derived class called DesktopDisplay to update any desktop apps or tools of the change in temperature. Each class is a derived class of the iObserver interface and implements the update method from that interface. The update method passes the temperature as a parameter and writes the temperature to the console in a message. To use the observer in the program, the developer creates new instances of weather station, phone display, and desktop display objects. Then they call the register observer method on the weather station object to register a new observer for each object. They pass in the phone display and desktop display objects as parameters when they call this method. Now to update each display, they simply call the setTemperature method on the weather station object, passing in a new temperature. The iObserver interface along with the subject class will update all displays with the new temperature. These patterns are ways that developers can simplify code and make it easier to maintain. Design patterns provide developers with blueprints for creating well-formed, readable, and extensible code. In this video, you learned how to recognize and describe key design patterns like singleton, factory, and observer. These patterns are essential tools that help you write code that's efficient, easy to maintain, and built to last. Imagine you're an architect with a blueprint in hand. This blueprint outlines every detail of the house you're about to build, from the number of rooms to the placement of windows. But until you actually start building, that house just remains an idea on paper. In programming, classes in C# work much the same way. They're blueprints that define how objects will look and behave, but they need to be built before they can be used. In this video, you will learn how to implement classes and objects in C#. Let's briefly review what a class is and what they contain. A class is a blueprint or template that shares characteristics and behaviors for a group of related objects. Classes include properties. These are pieces of data an object holds, like a person's name or age. They also include methods, which are the actions an object can perform, such as displaying information. And finally, constructors are the special methods that initialize the object when it's created. With these key elements defined, let's now dive into the specific syntax used to define a class in C#. To define a class in C#, you follow a clear sequence of steps. First, start by declaring the class with an access modifier such as public or protected. This tells C# who can access the class. Next, you use the class keyword followed by the name of your class. This is how you identify the class in your code. Then you'll open the class body with a pair of curly braces. Inside those braces, you'll define the key components of your class, properties which store data, constructors which set up the class, and methods which describe what the class can do. Suppose a developer wants to define a person class with a property, name, and age, a constructor to initialize these properties, and a method to display the person's information. To define this class in C#, start by declaring it with the public access modifier, followed by the class keyword and the name person. Next, open the class body with a curly brace and close it with another curly brace at the end. Inside this body, add a string property named name and an integer property named age. Additionally, the class includes a constructor method with the same name as the class, which initializes the properties using two parameters, a string called name and an integer called age. To distinguish between the property and the parameter, The property names are capitalized and the input parameters are not. Finally, the class has a method called displayInfo, which writes the name and age to the console. Classes in object-oriented programming by themselves can't do much work. A programmer can't process data, interact with the user, or send API calls. In order for a class to do work, you need to create an object from it. This process is called instantiation. Let's see how that process works in C#. Instantiation comes from the word instance and refers to the process of bringing a class to life by creating a working version of it. Think of it like using a cookie cutter. The class is the cutter, and each cookie you create is an object. We call this working version an object. With this approach, you can create as many objects as you need from one class, just like you make multiple cookies from the same cutter. Now let's see how you can create an instance of the person class and start working with it in C#. When instantiating the person class, the developer first declares a variable of the type person, naming it neighbor. C# is a type-safe language, meaning all variables must be declared with a specific type, ensuring clarity about what they can store. The variable neighbor can only hold person objects. Now that the developer has declared the variable, they can create a person object and assign it to the variable. They use the new keyword, followed by the class constructor, which is a method and therefore followed by parentheses. The constructor requires a parameter with the type string for the name and a parameter with the type int for the age. In this case, they pass John Doe for the name and 30 for the age as parameters to the constructor. The neighbor variable now contains an instance of the person class, or a person object. Recall that the person class included the properties name and age. These properties were declared with a public access modifier. This means that they are accessible by code from the object once the class has been instantiated using dot notation. In what follows, you'll learn about dot notation and how to use it in C#. Dot notation is syntax used to access members of an object such as properties, methods, and fields. Once an object has been instantiated, developers can reference their public members using a period or dot, followed by the property or method name. Let's apply the syntax to the person object. Since the variable neighbor holds the instantiated person object, a developer can reference its members by using dot notation. Suppose after the object has been instantiated, the developer needs to update the person's age. They can set the person object's age value using neighbor.age, changing it from 30 to 31. The developer also can call any of the object's public methods using dot notation. For example, to call the object's displayInfo method, the developer would write neighbor.displayInfo followed by empty parentheses. Classes in C# give the developer a lot of flexibility when working with code and helps them avoid redundancy. As an object-oriented language, classes are a foundational part of C#. In this video, you learned how to implement classes and objects in C#. We defined a class with properties, constructors, and methods, and instantiated objects from this class. Using classes is an important first step to building object-oriented programs. Using classes is an important first step to building object-oriented programs in C#. In C#, a class is like a blueprint for creating objects. It defines what properties, attributes, and methods, actions, the objects created from the class will have. For instance, if we have a class called person, each person object we create will have the properties and methods defined in this class. Properties are like the characteristics of the class. In this case, we want each person to have a name and an age, which describes a person. A class encapsulates these properties so they can be used to create specific objects that hold real data. To use our person class, we need to create an object from it. An object is an instance of a class, meaning it's an actual representation of the class that we can work with within our program. To create an object, we use the new keyword, followed by the class name in parentheses. This process is called instantiation. When we instantiate a class, we are creating a new object with its own set of properties and methods. Each object can have different values for its properties, even though they are created from the same class. Methods in a class define the behaviors or actions that an object can perform. While properties store information about the object, methods allow the object to do something. In our person class, we will create a method called greet that prints a message including the person's name. Think of methods as actions that an object can take. This method will use the name property to personalize the greet. To make an object perform an action, we call a method on it using dot notation. This means we write the object's name followed by a dot, and then the method name. For example, friend.greet calls the greet method on the friend object. When we call this method, it will execute the code inside it, which in this case prints a greeting that includes the person's name. This shows how we can interact with objects and make them perform actions using methods. You can create multiple objects from the same class, and each object will have its own set of properties. Even though friend and colleague are both instances of the person class, they are independent of each other and can have different values for their properties. This shows how a class can serve as a template for creating various objects with similar characteristics, but different data. Now let's create one more person object to see how each object behaves independently. As you have learned, mastering objects, classes, inheritance, and polymorphism is essential for writing adaptable and scalable code in C#. We began by exploring objects and classes, the fundamental building blocks of object-oriented programming. You discovered how these components help create a well-organized, reusable code structure. Next, we explored inheritance and polymorphism, focusing on how these concepts improve your application's adaptability and scalability. We explain their roles and why they are critical to object-oriented programming. Then we use practical examples in C# to show how these concepts operate in the real-world programming situations, providing hands-on practice to reinforce your understanding. After that, we examine common design patterns in OOP, focusing on how they solve frequent development challenges. You learn the best practices for effectively applying these patterns in different situations. Finally, we worked on implementing classes and objects in C# through structured exercises, helping you build confidence and mastery in applying OOP techniques. Understanding these object-oriented programming principles is essential for building robust and efficient applications. Mastering these concepts in C# will elevate your development skills and improve your ability to create scalable, maintainable code. Welcome to Asynchronous Programming in C#. This module covers the fundamentals of using async and awaits to improve application performance, develop practical solutions, and debug asynchronous code effectively. We begin by defining the core concepts of asynchronous programming and understanding their role in creating efficient, non-blocking applications. We'll explore how these concepts support smoother workflows and better resource management. Then you'll learn to implement async and await in C# programs, enabling you to handle tasks concurrently. You'll see how these tools optimize performance and responsiveness in your applications. Next, we'll develop practical asynchronous solutions, applying these techniques to real-world scenarios. You'll understand how to use these methods to address common challenges in software development. After that, we'll discuss the importance of asynchronous programming in modern applications, highlighting its impact on scalability and user experience. This will clarify why asynchronous techniques are critical in today's development environment. Finally, we'll examine the process of debugging asynchronous code and creating simple asynchronous programs, ensuring you can effectively troubleshoot and build reliable applications. By the end of this module, you'll have the skills to implement and debug asynchronous code, enhancing the performance and scalability of your applications. Let's begin our exploration of asynchronous programming in C#. Imagine you're at a busy restaurant. If the chef had to wait for each dish to cook before starting the next one, customers would wait too long for their meals. Instead, the chef starts a dish, sets it to cook, and then begins another. This way, multiple dishes are prepared in parallel, making the process efficient and fast. Asynchronous programming works similarly in the world of coding. In this video, you will learn how to explain the basic concepts of asynchronous programming. Asynchronous programming is a technique that allows tasks to run independently of the main program flow, enabling the program to start new tasks without waiting for the previous ones to complete. By enabling tasks to run in parallel, programs can be more responsive and perform background tasks at the same time users are doing other things in the application. Consider a scenario where you're building a web application. By using asynchronous programming, your program can fetch data from a server while still enabling users to interact with the user interface. This keeps your app fast and responsive, giving users a smoother experience. Without asynchronous programming, tasks would have to be completed in the order in which they were started. This is called synchronous programming. Next, we'll examine this technique and compare it with asynchronous programming. Synchronous programming is a technique where program tasks need to be completed in order, and a subsequent task can't start until the previous one is completed. Suppose you're building an application that has a series of forms that users have to fill out. After the user fills out a form, you want to make sure that the form has been fully processed before the user can move on to the next step. Using synchronous processing, each step in the process must complete before the next step can be started. In some scenarios, developers need to use synchronous programming in order to better control events. Asynchronous programming, however, has given developers the ability to improve application responsiveness and overall user experience. Let's compare both techniques. Even though developers use both asynchronous and synchronous programming techniques in applications, these techniques differ significantly in how they make a program operate. Both techniques can be designed to execute tasks in sequence. When needed, asynchronous programming can be structured to function similarly to synchronous programming. However, only with asynchronous programming can a developer perform tasks that don't block other tasks. Synchronous programming, on the other hand, doesn't allow developers to handle input and output tasks without waiting for them to complete. This capability is exclusive to asynchronous programming. Asynchronous programming also allows developers to run multiple tasks at the same time, which is a key advantage over synchronous programming. However, this benefit comes with added complexity. With synchronous programming, error handling is more straightforward and the program's execution flow is more predictable. In contrast, asynchronous tasks can make it harder to determine which process is running at a given time and which one caused an error. Imagine synchronous programming as a single row of dominoes falling in sequence, which is more straightforward to predict and troubleshoot. Asynchronous programming, however, is like multiple rows of dominoes falling simultaneously and converging unpredictably, making it harder to manage and diagnose issues. Finally, asynchronous programming techniques offer improved application responsiveness, efficiently use CPU resources, and scale effectively with many input and output tasks. These abilities are not native to synchronous programming. The technique a developer uses largely depends on the scenario. In many modern programming scenarios, asynchronous programming techniques can significantly enhance an application and improve the user's experience. Let's examine a few of these situations. Input and output or I/O operations, such as reading from or writing to a file, benefit from asynchronous programming. Using this technique, a program can start reading a file and continue executing other code while waiting for the file operation to complete. Another area where developers use asynchronous programming is when making network requests. Fetching data from an API or sending data over the internet often involve delays. Asynchronous programming allows the rest of the application to run smoothly while waiting for these requests to complete. Finally, developers improve the responsiveness of their applications using asynchronous programming. By not blocking the main execution flow, asynchronous programming ensures that applications remain responsive to user inputs, even when performing time-consuming tasks in the background. For example, a chat application can send and receive messages without freezing the user interface. Asynchronous programming has made modern applications more responsive and efficient, allowing them to accomplish much more in the same amount of time compared to older methods. Although it can involve some complexity, the benefits usually far outweigh the challenges in most cases. In this video, you learned how to explain the basic concepts of asynchronous programming. Asynchronous programming is a powerful technique that improves the efficiency and responsiveness of applications. By understanding and implementing these concepts, you can build applications that provide a better user experience and handle tasks more efficiently. Suppose you're working on a project with multiple tasks that need to be completed simultaneously, like compiling a report while waiting for data analysis to finish. In software development, asynchronous programming works similarly, allowing different parts of an application to run independently without waiting for another. This approach improves efficiency and user experience, but it also introduces challenges such as managing timing and maintaining smooth operation. In this video, you will learn to describe the benefits and challenges of using asynchronous programming. Asynchronous programming is a technique that allows tasks to run independently of the main program flow, enabling the program to start new tasks without waiting for the previous ones to complete. Asynchronous programming prevents the main applications from getting bogged down by long-running tasks, making the user experience smoother and more efficient. Let's explore these and other benefits of asynchronous programming in some detail. First, asynchronous code prevents the main application from getting blocked. This means that users can work in the app and perform other operations when a long-running operation is working in the background. When code is not asynchronous, only one operation can be running at a time. The application may appear to be frozen even though it's actually working on something. With asynchronous programming, delays like these are minimized. Many operations can happen at the same time, preventing the system from being blocked by any one operation. Second, asynchronous code tends to perform better, allowing multiple operations to happen simultaneously. Users experience this benefit as faster internet-based operations, a responsive user interface, and an ability to do more things in less time. A third benefit is that asynchronous programming better integrates with backend services because it handles data transfer efficiently. An application can retrieve data from many different locations at once and process that data as it comes in rather than having to wait for a previous operation to complete. For example, suppose an app needs to fetch information related to a user's account from one server while updating the user's account information in a database on another server. It can perform both operations simultaneously, giving the user a better overall experience. While asynchronous programming offers great benefits, it also introduces challenges that developers need to navigate. Let's explore these challenges. The first challenge developers face when using asynchronous programming is managing concurrent operations. Application code has to handle multiple operations at the same time without causing conflicts or delaying other code that is dependent on it. For example, if one asynchronous code block is dependent on data that comes from another, the second code block has to return the data before the first one can run. Even though both are run asynchronously, the developer has to make sure they run in a specific order. Next, asynchronous code can make debugging difficult. Asynchronous code can return from an operation while other code is running. Developers may not be able to catch errors or determine which code caused an error. It's similar to driving down a freeway and concentrating on the road in front of you. There are other cars all around you that require your attention, and when too much is going on, it can be difficult to know what to focus on. A final challenge is keeping the code readable, especially when managing complex asynchronous operations. Asynchronous code can become complex and harder to understand. When an operation occurs asynchronously, developers need to keep track of what happens when the operation ends, and what else might be occurring during the time the operation is running. Even experienced developers can lose track of the order of operations, making the code harder to read. In general, asynchronous programming offers developers and users with a lot of benefits. However, you should be aware that asynchronous programming is not without its challenges. By being informed of both, you can make solid decisions about how to structure your code to make it the best it possibly can be. In this video, you learned to describe the benefits and challenges of using asynchronous programming. Asynchronous programming offers significant benefits like non-blocking operations, improved performance, and better integration with backend services. However, it also presents challenges such as managing concurrency, debugging difficulties, and maintaining readable code. By understanding and addressing these challenges, developers can leverage the full potential of asynchronous programming. Imagine you're working with an app and suddenly everything freezes because it's loading data. Frustrating, right? In today's fast-paced digital world, waiting for an app to catch up is more than just annoying. It's a problem that can drive users away. But what if your app could be running smoothly even while handling complex tasks in the background? That's exactly what asynchronous programming with async and await in C# can do. In this video, you'll learn to explain the syntax and usage of async and await keywords in C#. Let's start with async, a concept that's key to making your apps faster and more responsive. The async keyword is a modifier that makes a method asynchronous. This means the method can perform tasks in the background without freezing the main application. The async keyword in C# is like setting up a separate worker to handle time-consuming tasks without disturbing the main flow of your application. For example, imagine you're at a restaurant. You place an order and instead of waiting at the counter, you sit down while the chef prepares your meal. That's what async does. It lets your code move on to other things while it works on a background task. First, to use the async keyword in C#, you start with declaring a method with the public access modifier. Next, add the async keyword to signal that this method will handle asynchronous tasks. Then follow it with the task return type to define the method's output. The async keyword tells the compiler that this method will perform asynchronous work, allowing it to run in the background. Now, with this overview of how async can keep your apps responsive by running tasks in the background, let's look at the await keyword. Await works hand in hand with async, helping you manage when these background tasks should finish before moving on. You use the await keyword to control program flow by waiting for a background task to happen before moving on to the next block of code. Await is a keyword that pauses the execution of the method until the awaited task completes. This causes your app to wait for necessary data or operations to finish, but only where it's needed, keeping the rest of the app running smoothly. First, when you use the await keyword, the method that contains the await is suspended, and control is given to the method that you're calling. Then, once the awaited task completes, the method resumes execution from the point right after the await. Think of await as a sign that tells the workers, hold on a moment, let me finish this task before we proceed. It's similar to experiencing a meal at a restaurant. When your meal arrives at the restaurant, you pause chatting and start eating. It's a pause, but only enough to eat. Next, you place the await keyword before the method that returns a task. You use the await keyword before get data from API. This pauses the execution of the current method until the get data from API task completes. The await keyword allows your application to handle other tasks while waiting for the result so your app stays responsive. In this video, you learn to explain the syntax and usage of the async and await keywords in C#. By running tasks in the background and strategically pausing execution, your app can handle complex operations smoothly and efficiently. Imagine you're building a modern app that needs to handle multiple tasks at once, like fetching data, processing files, and responding to user interactions. How can you ensure your app doesn't freeze or slow down under this load? The key is mastering async and await in C#, tools that allow you to keep your app running smoothly while handling time-consuming operations in the background. These tools are like the conductor of an orchestra, ensuring every section plays in harmony without missing a beat, no matter how complex the piece. In this video, we will implement async and await in C# programs. Using practical examples, you'll learn how these keywords are used in real-world scenarios. Async and await are used to simplify asynchronous programming in C#. Async marks a method as asynchronous. Await pauses the execution of the method that called the asynchronous task until the task completes, but it doesn't block the main program, allowing it to continue running other code. Asynchronous operations use the task type in C#. The task type is a way to represent work that will be done in the future without blocking the main program. Think of it as a placeholder for a value that isn't available yet. This value could be the result of some computation, a file operation, or any other action that takes time to complete. You use the async and await keywords along with the task type to perform asynchronous operations. Now let's explore some examples of how these keywords are used in C#. We'll start with simulating a delayed operation. First, declare a public asynchronous task method called simulateDelay using the async keyword. Inside the method, use the await keyword with a command that will pause the task for a period of time to simulate an operation that takes time. We can do this with the command task.delay5000. The delay command on the task object takes numbers in 1/1000th of a second. After the delay, the method prints operation completed after 5 seconds to the console. The delay in this example simulates a time-consuming task like retrieving data from a cloud-based database without blocking the main program. Now let's explore how to use async for file operations. Retrieving file data can sometimes take time, and you can use async to perform this operation in the background. To read a file asynchronously, first you declare a public asynchronous method called readFileAsync, which takes a file path as a parameter. In this method, we'll use a lot of special code that reads data from a file. You don't need to focus on that special code right now. We're just using this code to illustrate how the await keyword works. Next, inside the method, use a stream reader to open the file. Use the await keyword with read to end async to read the entire contents of the file asynchronously. Finally, after reading the file, the method prints the file contents to the console. In this example, the async keyword will get the file in the background task, but the await keyword will make sure that the contents aren't written to the console until the program has gotten to the entire file. These examples show how to perform a single operation using async and await. C# also provides the capability to perform multiple async operations in a single method and only return control back to the calling method after the operations have completed. Let's examine how to use async to accomplish this. To handle multiple async operations concurrently, first you declare a public asynchronous method called getDataFromMultipleSources. Next, inside the method, you create two tasks using the getDataFromAPI method, each fetching data from a different API endpoint. Finally, use task_whenAll with the await keyword to wait for both tasks to complete simultaneously. Once both tasks are finished, print the results of each task to the console. By using whenAll, you're telling the async operation to wait until all the operations being managed to finish before proceeding. This approach efficiently handles multiple async operations without blocking the main program. The more async operations you perform in a single method, the greater the chance something will not go as planned. Handling errors will keep your async operations from creating critical bugs in your program. You can use special code called a try-catch block. Think of a try-catch block as a safety net. The code you want to run is put into the try portion of the block of the code. If it runs without an error, the catch portion never runs. If an error occurs in the try portion, the catch portion catches it and allows you to handle it. This can prevent your program from breaking when an error occurs. You can use try-catch blocks in any code, but we'll examine a code sample that implements this error handling code in async methods. To handle potential errors in an async method, first you declare a public asynchronous method called getDataWithHandling. Next, inside the method, you use a try-catch block to handle exceptions. In the try block, create an HTTP client object and use the await keyword with getStringAsync to fetch data from an API. If the result is successful, print the data to the console. If an HTTP request exception occurs, the catch block will handle it by printing an error message with the exception details. By using try-catch blocks in your C# async methods, your program will handle errors gracefully. With these examples, you've seen how async and await can help manage asynchronous operations in C# programs. By practicing these concepts, you'll be able to write more responsive and efficient applications. In this video, you learned to implement async and await in C# programs. Using async with await makes your applications responsive. C# enables you to perform multiple async operations in a single method and wait until all of them are complete before performing another operation. You can also catch and handle errors in async operations, keeping your async code running efficiently and without disruption. start, let's understand what asynchronous programming is. Asynchronous programming allows your application to perform tasks without waiting for others to complete. This is useful when working with operations that take a long time, like downloading a file or accessing a database, allowing your program to stay responsive and handle multiple tasks simultaneously. In synchronous programming, tasks are performed one at a time, meaning the program has to wait for each task to finish before moving on to the next one. This can make your program slow, especially if it's waiting for a task like downloading data from the internet. Asynchronous programming, however, lets your program start a task and then move on to do other work while waiting for the task to complete. This is done using async and await in C#. We use the async keyword to define a method as asynchronous, and we use await within that method to mark points where the program can pause and wait for a task to complete. The key benefit is that your program remains responsive and can handle other operations while waiting for tasks to finish. In this step, we'll create a simple asynchronous method. The method will simulate a task that takes some time to complete, like downloading data. This will give you an idea of how async and await work. We start by creating a method named downloadDataAsync that is marked with the async keyword. This indicates that the method will run asynchronously. Inside this method, we use await to simulate a delay, representing the time it would take to download data. This delay doesn't block the main program from running other tasks, thanks to the await keyword. Now that we have an asynchronous method, the next step is to call this method from the main method. We'll observe how the program doesn't wait for the download to finish before moving on to other tasks. When calling an asynchronous method, we use the await keyword in front of it to tell the program to wait for the method to complete before continuing. However, because the method is asynchronous, this doesn't block other parts of the program from running. This means you can run out of the code while waiting for the download to complete. This is where the power of asynchronous programming shines, allowing you to keep the application responsive. Next, we'll see how to run multiple asynchronous methods in parallel, allowing them to run simultaneously without waiting for each other to complete. This is useful for tasks that can be performed independently, like downloading multiple files. When you have multiple asynchronous methods, you can call them in parallel using task.waitOn. This method waits for all the tasks to complete before continuing, but allows them to run simultaneously. This can significantly improve the efficiency of your program, especially when dealing with tasks that take a long time to complete. By running tasks concurrently, you can save time and make better use of system resources. Finally, let's add error handling to our asynchronous methods. When working with async code, it's important to catch exceptions that may occur during the execution of tasks to prevent the application from crashing unexpectedly. In asynchronous methods, you can use try-catch blocks to handle exceptions just like in synchronous code. However, since async methods return a task, if an exception is thrown, it gets stored in the task object. We use a try-catch block around await calls to catch these exceptions. This allows us to handle errors gracefully and provide meaningful feedback to the user instead of the application crashing or becoming unresponsive. Imagine you're using a popular app and it's taking forever to load. You're frustrated tapping the screen waiting for something, anything to happen. Now think about the apps that work flawlessly even when dealing with complex tasks in the background. What's the difference? In today's fast-paced world, users expect their software to be quick and responsive no matter how complex the operations behind the scenes. That's where asynchronous programming comes into play. In this video, you'll learn to describe how to design practical async solutions. Async programming is a programming paradigm that allows tasks to run independently of the main program flow, enabling non-blocking operations. Async programming improves application responsiveness and efficiency, especially when dealing with input and output operations like API calls and file processing. You can use specific asynchronous programming techniques when developing a software solution. These techniques provide practical improvements to your solutions that improve the user's experience. Let's explore some ways you can use asynchronous programming to improve your software. First, by using asynchronous programming, you can handle multiple API calls efficiently. One technique is to use asynchronous programming methods to make multiple API requests concurrently rather than one after the other. For example, when you're fetching data from several APIs for a dashboard, use asynchronous calls to request all the data at once, which reduces the overall time the application takes to get the data. But it's not just about making the calls. How you handle their responses also matters. Another technique is to handle responses efficiently by processing each response as it arrives without waiting for all the requests to complete. For instance, you can design a program to display partial data on a dashboard as it becomes available rather than waiting for all the data the dashboard will show to arrive. This improves the user experience by showing information progressively. Just as asynchronous techniques can optimize API handling, they can also greatly improve your app's performance when working with large data sets. One approach is to split large data sets into smaller chunks and then process them asynchronously. An example of this technique in a practical situation is to process large CSV files in chunks to avoid blocking the main program. This allows the application to remain responsive while the program works through the large amount of data. Another asynchronous approach you can use to process large data sets is to use async libraries. These are packages of code that are designed to manage large data sets efficiently. Many times these libraries are shared and free to use and modify. For example, the Async.io Python library is designed to handle large data processing tasks concurrently using asynchronous programming techniques. Finally, let's explore ways you can use asynchronous programming to enhance your application's responsiveness. One technique is to use async methods that don't block the UI. This involves implementing asynchronous operations that keep the user interface responsive while your application is performing background tasks. For example, suppose you're writing a chat application. You can avoid blocking the app's UI and keeping it responsive by sending and receiving messages asynchronously. Another technique is to use asynchronous programming to maximize how the program uses system resources. Asynchronous operations help your program avoid wasting time and make better use of system resources. This approach helps improve the overall performance of an application by using resources more efficiently. For example, you can design a web server to handle multiple client requests simultaneously through asynchronous programming, which increases the server's capacity to respond quickly and efficiently to each request. Not every situation calls for asynchronous programming techniques. But when you're designing a software solution, look for scenarios where you have to process multiple API calls, handle large data sets, or manage the user interface. Consider how using asynchronous programming can improve how your application performs in these situations. In this video, you learned how to design practical asynchronous software solutions. Developers use asynchronous programming to handle multiple API calls, process large data sets, and improve application responsiveness. By using these techniques, you can build more efficient and responsive software solutions. Imagine you're on the verge of completing an online purchase only to have the app freeze just as you click Buy Now. You get frustrated as you wait, uncertain if your order went through or not. Ever wondered why this happens and how developers can prevent it? These moments of frustration aren't just inconvenient, they're a sign of inefficient task management in the app. To make apps operate more smoothly, developers turn to a powerful solution, asynchronous programming. This approach allows applications to stay responsive and efficient even when handling complex or time-consuming operations. In this video, you'll learn to develop practical asynchronous programming solutions. Let's begin by setting up a basic C# console application that simulates a data fetching scenario for Groove Eco, a company offering eco-friendly products. First, you define an asynchronous method, fetch products async. The async keyword before the return type signals that the method is asynchronous. Next, inside the method, task delay 2000 simulates a 2-second delay, imitating an API call. Finally, after the delay, the method returns a list of products including EcoBag and reusable straw. The await keyword pauses the method execution until the delay is complete ensuring the main thread isn't blocked. Now that we've created the asynchronous method, let's explore how to call it using the await keyword so the method completes before continuing. First, create a method called displayProductsAsync, which also uses the async keyword. Inside the method, call the method fetchProductsAsync using the await keyword. By using await, the method waits for the products to be fetched before continuing. Then it loops through the list of products and prints each product name to the console. By using this approach, the UI remains responsive while data is fetched in the background. With the async methods in place, we'll add error handling so that the application remains stable even if something goes wrong. First, update the fetchProductsAsync method by adding a try-catch block to handle errors. If an exception occurs during the API call simulation, the catch block will display an error message using console.writeLine. The method will then return an empty list, ensuring the application doesn't crash. This approach makes your code more robust and ready for real-world scenarios. Now that we've handled errors, let's add code to run multiple asynchronous tasks concurrently. We can improve this application by fetching product data and reviews simultaneously, and we'll use async functions in C# to accomplish this. Create a method called fetchDataAsync, which calls fetchProductsAsync, and a new method called fetchReviewsAsync, which gets product reviews from a database. The return values from these methods are stored in variables. You use the task_WhenAll function to wait for both tasks to complete before proceeding to the next block of code. This approach improves the application's efficiency by enabling tasks to run in parallel. In this video, you learned to develop practical asynchronous programming solutions using C#. Our solution for Groove Eco's products website involved fetching product data asynchronously to keep the application responsive. We created an async method, handled errors, and ran multiple tasks simultaneously, ensuring the app remained efficient. Imagine you're using a fitness app that not only tracks your workouts, but also instantly responds to every tap, swipe, and input. Unlike apps that lag, freeze, or force you to wait for a task to complete before moving on, this fitness app has no delays, no frustrating loading screens, just a smooth, seamless experience. How does this happen, especially when the app is busy syncing your data, fetching your personalized workout plans, and even communicating with your wearable devices? The secret lies in asynchronous programming. In this video, you'll learn to explain the role of asynchronous programming in modern software development. Asynchronous programming enhances user experiences and addresses performance bottlenecks that were common in previous programming models. Asynchronous programming is a technique that allows multiple tasks to run simultaneously without blocking the main application. Using this approach makes software efficient and responsive. Let's build on this overview of asynchronous programming by exploring some real-world scenarios in which it has significant impact. First, let's consider a web application like a web portal for a fitness company called FitWave. By using the power of asynchronous programming, the website can handle multiple user requests simultaneously. It also can update portions of a web page without having to refresh the entire page. For example, when users submit workout data or check their progress, asynchronous operations allow the server to process these requests at the same time, ensuring a fast and responsive experience. Just as web applications benefit from asynchronous programming, mobile applications improve significantly when developers use this technique to build them. You can use asynchronous programming in a mobile app so that background tasks like syncing data or fetching workout plans don't disrupt the user's primary interactions with the app. FitWave's mobile app, for instance, uses asynchronous programming processes to update the fitness goals in the background while the user continues to navigate the app smoothly. Finally, in addition to enhancing user-facing applications, asynchronous programming also plays a role in data analysis, enabling faster and more efficient processing. Applications and websites generate and use a lot of data. Data analytics is the process of examining this data to find insights. High-performance systems, such as those analyzing large datasets for personalized workout recommendations, benefit from asynchronous programming. By processing data concurrently, FitWave can analyze user performance in real time, and provide immediate feedback without delays. Now that we've explored some application scenarios, let's review the performance benefits of asynchronous programming. First, asynchronous programming enables non-blocking operations. This means that the users can work in the app and perform other operations when a long-running operation is working in the background. Tasks like loading workout data or downloading videos don't freeze the app, allowing it to continue running smoothly while these operations occur in the background. This improves the overall user experience. Second, asynchronous programming allows you to create applications that support multiple operations running simultaneously, which can help applications do more with the same resources. For example, FitWave can update workout stats while syncing with a wearable device, ensuring real-time feedback that keeps users engaged and motivated. Third, asynchronous programming optimizes resource use. By not waiting for one task to finish before starting another, apps like FitWave can handle more users and tasks without slowing down. This improves scalability and reliability, especially during peak usage times. In this video, you learned to explain the role of asynchronous programming in modern software development. By enhancing user experiences and addressing performance bottlenecks, asynchronous programming is a technology you can use to build efficient, high-performing applications. Think of a scenario where your application suddenly has to manage a surge of thousands of users at once. How do you ensure it doesn't crash, slow down, or frustrate your users? The secret lies in how you manage tasks behind the scenes. Asynchronous programming isn't just a technical buzzword, it's a critical skill that allows your application to handle multiple tasks at once, maintaining speed and responsiveness. Mastering this approach can be the difference between a smooth, efficient app and one that struggles under pressure. In this video, you will learn to describe industry examples and best practices of asynchronous programming. First, let's review what asynchronous programming is. Asynchronous programming is a technique that allows computing tasks to run independently of the main program flow, enabling the program to start new tasks without waiting for the previous ones to complete. Asynchronous programming improves the performance and scalability of applications, particularly in environments that have a lot of users or make a lot of calls to remote servers. Now let's explore how companies use asynchronous programming to make their applications better for users, starting with the telemedicine platform HHAI. HHAI uses asynchronous programming to handle multiple API calls and real-time data processing. By using asynchronous keywords like async and await in their code, HHAI's website can fetch patient data, health records, and appointment schedules simultaneously, reducing wait times and improving user experience. For example, when a doctor accesses a patient's profile, the application receives medical history, recent test results, and upcoming appointments, all at the same time, so users don't have to wait for data to load. Using asynchronous programming techniques to improve API calls isn't the only area the technology can help developers. Let's examine how an e-commerce platform uses asynchronous programming in their app ecosystem. Groove Eco uses asynchronous programming to enhance the performance of its mobile application. By using asynchronous programming techniques, Groove Eco's developers enable their mobile users to perform common tasks like browsing products and adding items to their cart without experiencing delays. For instance, when a user scrolls through a product listing, images and details load in the background as the user scrolls, providing a smooth and uninterrupted mobile experience. In addition to improving the performance of websites and mobile apps, companies use asynchronous programming to optimize cloud services. Let's examine ways a cloud storage service might improve its file transfer services. CloudBreeze, a cloud storage service, uses asynchronous programming to manage reading and writing files from its service more efficiently. It uses asynchronous methods in its code to handle multiple file uploads and downloads concurrently. This optimizes server performance and reduces the time it takes for users to access their files. Users experience this optimization when they upload large files in the background. Even though the file is large and can take time to upload, they can continue to use other features of the application, so their experience with the service is responsive and uninterrupted. Developers use asynchronous programming to make apps and services responsive and efficient. By applying time-tested asynchronous programming techniques to their code, they are able to create great user experiences. These techniques are called best practices, and they contribute to creating consistent asynchronous code. Let's examine some of these best practices, starting with simplifying code. First, use async and await to make asynchronous code simpler to read and maintain. Before asynchronous code, developers had to use special functions called callbacks that could create complicated chains of code that were hard to manage and debug. Async functions improve code clarity and reduce errors. Second, always include proper error handling in asynchronous operations to manage potential failures gracefully. For example, you should use try-catch blocks within async functions to handle errors and provide meaningful feedback to the user. Third, be sure to efficiently use the resources on the device on which the asynchronous code is running. Efficient code limits the number of asynchronous tasks that run at the same time. One way to accomplish this is to build a task queue that manages and controls how many asynchronous tasks that can run at a given time. This helps you maintain optimal performance and avoid using excessive resources on the computer. Fourth, design your application to perform operations that send or receive data asynchronously. This avoids blocking the main application. To accomplish this, you can use specialized asynchronous code libraries that allow the app to continue working smoothly even during heavy data processing operations. Asynchronous programming techniques can be a powerful addition to your coding toolbox. By using best practices to implement asynchronous code, you can create apps that are efficient, scalable, and fast. In this video, you'll learn to describe industry examples and best practices of asynchronous programming. Asynchronous programming has become an industry standard for creating applications that perform well in many situations. In a cloud-connected mobile world, asynchronous code isn't merely an option, but a necessity. When asynchronous code fails, it doesn't just cause small problems. It can completely derail your project. Bugs can hide in places you'd never expect, surfacing at the worst possible times and leaving you scrambling to figure out what went wrong. The unpredictable nature of asynchronous operations makes debugging a critical skill to master, especially when deadlines loom. By using the right tools and strategies, you can efficiently identify and fix issues in your code. Let's explore essential techniques and tools for debugging asynchronous code effectively. In this video, you will learn to develop skills in debugging asynchronous code. Let's begin by reviewing what asynchronous code is. Asynchronous code runs independently of the main program flow, enabling the program to start new operations called tasks. Tasks run without having to wait for the previous ones to complete. Because tasks run independently, debugging them requires specific techniques so you can determine not only where in the code the bugs are, but also when they're occurring. Next, let's explore the challenges developers face when debugging asynchronous code and how to overcome them. We'll start with nonlinear execution. First, because asynchronous code does not run in a specific sequence, its nonlinear execution makes it harder to trace what tasks are running and when they will finish their job. Second, errors in asynchronous code may not be immediately apparent, leading to silent failures. Because asynchronous code runs in the background, the main program may continue to run, making everything seem normal. Only when you experience a symptom because the asynchronous task failed will you become aware that something went wrong. Third, debugging issues that occur when tasks run at the same time can be especially challenging. One example is a race condition, which happens when two or more tasks try to access resources they both share at the same time. This can lead to unpredictable results. It also can make it difficult to trace where the problem is happening because the order of execution can change each time the program runs. As a result, bugs may not always occur in the same way, making it hard to figure out what caused them and how to fix them. Next, let's explore common debugging techniques that developers use to find issues in asynchronous code. We'll start with using breakpoints to inspect code. To debug asynchronous code, you first can use breakpoints to pause the execution of your code at specific lines of code. When the program is paused, you can inspect the state of the application at that moment. You can examine the value of variables, inspect what code just ran, and what code is about to run. When asynchronous code is running independently of the main program, you can set breakpoints in the main program and in the asynchronous code so you can learn which part of your code is causing the bug. A second technique for debugging asynchronous code is to check the status of the tasks you started to understand if they're pending, running, completed, or if they failed to complete their job. In C#, you can inspect tasks by checking their status property, which indicates the current state. By logging their states or using debugging tools to set breakpoints and inspect the task state, you can determine if it's failed for any reason. Third, you can find bugs by handling potential errors in your asynchronous code. This involves wrapping asynchronous code in expressions that will prevent the code from crashing your program. It traps the bug before it can do harm. When you implement proper error handling, your code will catch the error in asynchronous tasks, and you can create a log entry that tells you what happened. Because the code automatically traps these bugs, you don't have to set breakpoints and analyze the code closely. You can inspect the logs that the program is running and check if an error has occurred. Modern programming tools like Visual Studio Code have features that can assist you in debugging asynchronous code. Let's explore some of those now, starting with the Visual Studio Code debugger. The first feature in Visual Studio Code is available through an extension. The official C# extension from Microsoft enables you to debug asynchronous code. After installing the extension, you can set breakpoints, step through code, and inspect variables and running tasks directly within the editor to debug async methods and task objects. The second feature, the Task Explorer extension, enables you to monitor and manage tasks in your code. Task Explorer helps you inspect the status of asynchronous tasks, making it easier to identify and troubleshoot issues. Log points are a third feature that you can use to debug your asynchronous code. Instead of breakpoints, log points log variable values and messages to the console without pausing the program. This enables you to get information about asynchronous tasks while they're running. A fourth and final feature is called the call stack tool. This tool lets you follow the sequence of method calls, including asynchronous ones. In the debugger, you can use the call stack pane to trace how the program runs and analyze the order in which the asynchronous methods are called. Pairing these Visual Studio Code tools with debugging techniques can help you overcome the challenges of debugging asynchronous code. In this video, you developed skills in debugging asynchronous code. We explored common debugging techniques, discussed the challenges and solutions in debugging async code, and looked at the tools in Visual Studio Code that aid in this process. By mastering these techniques and tools, you can efficiently debug asynchronous code and ensure your applications run smoothly.
In this lab, we'll be working with a simple application that will allow us to simulate and demonstrate an async operation. We're going to use task delay to simulate data coming in and going out of a server, but the delay just shows how the async works. And we're going to use a simple console application that I created using the .NET new console template. In step one, we're just reviewing the async and await keywords. And these allow us to perform operations in the background and essentially multitask where it doesn't block the application from doing other things. So when we have to retrieve data from a server, we have some long running process like processing data. We can do it asynchronously, so it's running in the background while the user is able to perform other tasks like interact with the UI, scroll, whatever, in the other part of the application. So these are very powerful modern techniques to use when you're programming. Now in step two, we're going to implement the asynchronous method. And in my application, I just have the program.cs file that I'm working with. And I have method perform long operations async. We have the async and task keywords here, which are important to use when you're performing asynchronous operations. So we're specifying and telling the program these are async operations. And we want you to create a task when you're working with these operations. And you can create multiple tasks and then manage them. And that's why we specify it as a task. This method is very simple. It writes out to the console that an operation started. We give it a delay of about 3 seconds, and then we write that the operation is completed. You can imagine where that await task.delay line is, or you go out to a server and you retrieve data, or you do a long-running operation like processing large amounts of data while the user is able to work elsewhere in the app. When we use our await, we're using the task keyword, and we're using the delay method on the task object to simulate that delay. And in step 3, we're going to call the async method. I'm going to move my code down here where we actually have the main method that we have in our program. And this is where we call it. We're using the task object again inside the main method. And we're using the async keyword. And we're telling it to await, or in other words, wait until the perform long operation async method has returned. So wait until that's done, and then go to the next line. And in this case, we're just writing out that the main method is completed. That task.run, the await keyword won't move to the next line until that task has been completed. Even though it's running in the background, it will wait to run that console.write line. When the application runs, it runs the main method in our program. It'll run that operation. Now let's go ahead and run this. And we should see those messages in our console. We have the operation started message below in our perform long operations async. Operation started, the operation completed after a delay, and then we had our main method completed line that ran. So the application ran as expected, and it simulated that async operation. In step 4, we're going to add a little bit to this method and handle errors. I just have this already written as a separate method here below called perform long operations 2, and we have our try catch block in this method. So the try will run first, and it will try to perform all the operations in that block of code. If something goes wrong, the catch block will run, and it will tell us what happened. In this case, we're catching the exception in the EX variable, and then we're printing out the message for that exception. In the try block, we're using the throw keyword to throw an exception. So obviously we don't necessarily want to do that in a real program. This is for, as a simulation, just to show what happens when we do produce an error. And that throw will actually simulate the error. In a real application, we might comment that out. In some cases, you may want to throw an exception so that you can actually capture any error that occurred. But in this case, we're just using it to simulate an error. So what we should see here is the operation started. We should never get to operation completed. This is dimmed out a little bit because Visual Studio Code is telling us that will never be hit because it'll always hit the throw new exception line before it gets to console write line. We have operation started. Then an error occurred with the message of what the error is, and then the main method completed. I'm going to change my method here to call our second method that we created with the error handling in it. I'll go ahead and run that again. The operation started. We have a simulated error, and then the main method completed. So all of our code ran. We had simulated error, and the message that it produced is that it is a simulated error, because that's what we passed into our throw command. We passed in simulated error, so that's what the message that's produced. In a real world scenario, that EX would capture the actual error that occurred in the application. So using async, you can perform what it would be like for an application to run in the background. So using the keywords async, task, and await, you can create these methods that perform operations in the background, which can make for a better user experience.
As you have discovered, mastering asynchronous programming is key to creating efficient, scalable, and responsive applications, which is essential in today's development landscape. We began by introducing the fundamental concepts of asynchronous programming and how they contribute to building efficient, non-blocking applications. You discovered how these principles enhance workflow efficiency and optimize resource use. Next, we explored using async and await in C# programs to manage tasks concurrently. You learned how these tools improve application performance and responsiveness. After that, we focused on creating practical asynchronous solutions and applied these techniques to real-world situations to overcome common software development challenges. We then examined the significance of asynchronous programming in modern applications, emphasizing its scalability and user experience enhancements. Lastly, we explored how to debug asynchronous code and create basic asynchronous programs, equipping you with the skills to troubleshoot effectively and develop reliable applications. Mastering asynchronous programming is essential for building efficient, scalable, responsive applications. Congratulations, you have completed asynchronous programming. Imagine having an AI-powered coding assistant that can understand your intent, generate code snippets, and even help you debug complex issues. This isn't science fiction, it's Microsoft Copilot, a revolutionary tool that's changing the landscape of software development. From boosting productivity to enhancing code quality, Copilot is transforming how developers work, making coding more efficient and accessible than ever. In this video, we will explain the key features of Microsoft Copilot. Microsoft Copilot is an AI-powered coding assistant that integrates seamlessly with your development environment. It's designed to enhance productivity by using advanced machine learning algorithms to provide intelligent code suggestions and automate repetitive tasks. Let's explore the key features that make Microsoft Copilot an indispensable tool for developers of all skill levels. First, let's examine how Copilot assists with code generation. This feature is at the heart of what makes Copilot so powerful and time-saving for developers. Copilot can generate entire functions or code blocks based on natural language descriptions or comments. As you type, it analyzes the context of your code and project, offering relevant suggestions that align with your coding style and project requirements. This capability significantly speeds up the coding process, allowing developers to focus on problem solving rather than syntax. Copilot doesn't just help with individual lines of code, it can suggest entire file structures, class hierarchies, and design patterns. By understanding your project's overall architecture, Copilot can recommend best practices for organizing your code, making it more maintainable and scalable. This feature is particularly helpful for developers starting new projects or refactoring existing ones. While developers spend most of their time creating code, they also spend a significant amount of time finding and fixing code flaws, which are known as bugs. Now let's examine how Microsoft Copilot helps developers debug code. When it comes to debugging, Copilot can be an invaluable ally. It can analyze error messages and suggest potential fixes. It also can identify common coding mistakes, even proposing more efficient algorithms. By using its vast knowledge base of coding patterns and best practices, Copilot can help you troubleshoot issues faster and write more robust code. Finally, we're going to explore how Microsoft Copilot integrates with development environments through GitHub Copilot. Both use the same core AI technology and are owned by Microsoft. GitHub Copilot is specifically focused on coding assistance and integrates directly with IDEs and code editors. This integration allows developers to access Copilot's features directly within their preferred and popular IDEs, such as Visual Studio Code, Visual Studio, and JetBrains IDE. The seamless integration means you can leverage Copilot's capabilities without disrupting your workflow. As you code, Copilot works in the background, offering suggestions and assistance, enhancing your productivity. In this video, you learned about the key features of Microsoft Copilot and how it integrates with development environments. With Copilot's code generation capabilities, assistance with application structure and organization, and debugging support, developers can enhance their productivity and code quality. As AI continues to evolve, tools like Microsoft Copilot are set to play an increasingly important role in the future of software development. Imagine having a tool that would make writing code smoother, faster, and nearly error-free. This tool is like a reliable assistant by your side, helping you navigate complex coding tasks with ease. This isn't a distant possibility, it's a reality that Microsoft Copilot brings to your coding tasks. From boosting your productivity to minimizing mistakes, the benefits are truly transformative for developers at every level. In this video, we will describe the benefits of using Microsoft Copilot for coding and debugging. Microsoft Copilot is an AI-powered assistant designed to enhance productivity by using advanced artificial intelligence to provide assistance, automate repetitive tasks, and offer intelligent suggestions. Microsoft Copilot can be used for many tasks, but it is especially helpful when developing software. Specifically, can help you be more efficient and productive and reduce errors in your code. Let's explore how Microsoft Copilot enhances coding efficiency and productivity by automating tasks that would otherwise consume valuable time. First, Microsoft Copilot provides automated code suggestions as you type. Copilot analyzes the context of your code and suggests the next line or even multiple lines of code, allowing you to code faster. Second, Copilot can take care of repetitive coding tasks such as writing code templates or setting up common functions. This reduces the time you spend on routine work, freeing you up to focus on more complex aspects of your project. When code is formatted properly, it's more readable and easier to maintain over time. Microsoft Copilot can help you structure and format your code by adding proper indentation, code comments, and streamlining code blocks. These improvements also can improve efficiency when you're working on writing code with others. Another significant benefit of using Microsoft Copilot is its ability to reduce errors and improve the quality of your code. Let's investigate how the tool can work alongside you to help you write better code, starting with its ability to give you feedback as you're coding. First, Microsoft Copilot provides real-time feedback on your code, highlighting potential errors as you type. This immediate feedback helps you catch mistakes early, reducing the likelihood of bugs making it into the final code base. Next, once Microsoft Copilot identifies potential errors, it offers suggestions to improve code quality. These suggestions are rooted in industry best practices you can follow to improve your code, which contributes to cleaner, more maintainable software. Microsoft Copilot can also help you identify code that might be causing bugs and help you develop solutions. You can describe the symptoms of a bug and include the code where the bug may be occurring. Microsoft Copilot can analyze the code along with the symptoms and describe where the code might be faulty. In this video, you learned to describe the benefits of using Microsoft Copilot for coding and debugging. By leveraging Microsoft Copilot, you can enhance your coding efficiency, reduce errors, and improve code quality, leading to better outcomes in your software projects. When it comes to coding, efficiency is key. Whether you're handling data, managing user input, or crafting algorithms, finding the right code snippet quickly can save you time and effort. But what if you could take that efficiency a step further? Microsoft Copilot is a tool that not only helps you generate code snippets on the fly, but also integrates them seamlessly into your projects, making your code cleaner and more robust. In this video, we will learn to demonstrate how to use Microsoft Copilot to generate C# code. Microsoft Copilot is an AI-powered tool that aids developers in generating and integrating code by providing intelligent code suggestions and automating common coding tasks. Let's explore what Microsoft Copilot can do for you, starting with the ways it can generate code. First, with Microsoft Copilot, you can generate code snippets for handling data, managing user input, and creating basic algorithms. For instance, if you need a function to validate user input, Microsoft Copilot can suggest the appropriate code based on your context. This allows you to focus on the broader aspects of your project while Copilot handles the repetitive coding tasks. For example, Microsoft Copilot can create C# code to check whether a person's age entered on a form is between 1 and 120. The code asks the person to enter their age. It then checks whether the age they entered is between that range. If it isn't, the algorithm prints the message, "Please enter a valid age between 1 and 120 to the console." If the age is between that range, the program prints "valid age" to the console. To get Microsoft Copilot to produce this code, you can use this prompt. You are building a basic console application in C#. The user needs to input their age, and you want to validate that the input is a number and is within a certain range, for example, 1 to 120. Generate the appropriate C# code to handle this. Second, Microsoft Copilot can assist in generating algorithms for basic operations such as sorting a list or calculating averages. It can generate entire functions, classes, or just small snippets to help you complete your code faster. This capability is particularly useful when you need to quickly implement basic functions that are an essential part of your application's logic. These snippets can be used as is or modified to suit your specific needs. Using the tool for these basic tasks can save you time in the development process. Suppose you want an algorithm to sort a set of numbers from lowest to highest. Microsoft Copilot can produce C# code that defines a variable called numberList that contains the numbers 5, 10, 2, 8, and 3. It then calls the sort function on that list and prints the sorted list to the console with the message sorted numbers are 2, 3, 5, 8, and 10. You can prompt Microsoft Copilot to produce this algorithm by prompting with this request. You are building a console application that needs to sort a list of integers and calculate the average of numbers in the list. Generate the appropriate C# code to perform both tasks. Generating code is just the beginning of how Microsoft Copilot can make your coding job easier. Once it generates code, it can integrate it directly into your existing project, ensuring consistency and reducing the risk of errors. Let's investigate how it does this. We'll start by examining how Microsoft Copilot can help you improve your code with suggestions. First, Microsoft Copilot can help you refactor and rewrite existing code to improve its structure or performance, a process called refactoring. It will suggest alternative approaches for building an algorithm or more efficient ways of doing something. By working with the tool, you can optimize your code and make sure it's maintainable. For example, suppose you have an algorithm that adds numbers between 1 and a number the user enters. You've written the code, but you want to make it more streamlined and easier to maintain. You can get assistance from Microsoft Copilot by asking it the following. I've written a piece of code that adds up all the numbers from 1 to a number entered by the user. Now I want to refactor it so that the code is easier to read and maintain. Generate a cleaner version of the code that still accomplishes the same task. You would then paste in your original code with this prompt, and Microsoft Copilot will refactor it for you. Finally, after generating and refactoring your code, Copilot can ensure that your new code integrates smoothly with your existing project. It maintains consistency with your existing code and even adds comments to help you understand and maintain your code base more easily. With Copilot, integrating new code into your project results in clean, well-organized code blocks that are easy to understand and maintain. This process minimizes the risk of introducing errors during integration. In this video, you learned to demonstrate how to use Microsoft Copilot to generate C# code. Using Microsoft Copilot to generate and integrate C# code can greatly enhance your development process, resulting in efficient, clean, and maintainable projects. Imagine you're working on a critical C# project and a bug derails your progress. Every developer faces this frustration, but what if there was a tool that could make debugging smoother, faster, and more intuitive? Enter Microsoft Copilot, a cutting-edge AI assistant designed to enhance your debugging process by offering real-time feedback, suggesting fixes, and helping you identify and correct issues with ease. In this video, we explain how to use Microsoft Copilot to debug C# code. Let's start by reviewing how Microsoft Copilot works. Microsoft Copilot is an AI-powered assistant that integrates into environments like Visual Studio Code and platforms like GitHub. It assists developers by offering real-time code suggestions, explanations, and debugging help. Now let's examine how Microsoft Copilot integrates with development environments like Visual Studio Code to assist with coding tasks. While you're writing C# code in Visual Studio Code, Microsoft Copilot monitors your code in real time. It automatically flags potential bugs, logic errors, or problematic patterns, helping you catch issues early without needing to paste code into a separate tool. But error detection in Visual Studio Code isn't the only way Microsoft Copilot can assist you. Let's explore how the tool can work alongside you when you're on source control platforms like GitHub. On GitHub, you can prompt Microsoft Copilot with questions or issues. First, the tool provides detailed feedback and suggests ways to fix potential errors. Next, you can get assistance by having Microsoft Copilot analyze code for issues or explore ways to improve pull requests. For example, when a developer submits a pull request, a PR, on GitHub, Microsoft Copilot can help review the changes. If you ask, are there any potential issues with this pull request? Microsoft Copilot will analyze the code differences in the PR, suggest improvements, point out potential bugs, highlight sections that may need more testing, and recommend additional tests to cover new code paths you introduced in the PR. Detecting errors is only the first step in maintaining clean, functional code. Beyond error detection, Microsoft Copilot also offers valuable assistance in debugging your code, helping you understand the causes of errors and suggesting fixes. Next, we'll examine how this tool helps with debugging. To start, Microsoft Copilot goes beyond error detection. When your code produces an error, it acts as an intelligent assistant, explaining what might be causing the problem. Next, for syntax or logic issues, it suggests possible fixes directly within your development environment. Moving on to more advanced debugging tasks, it can help you better troubleshoot complex bugs. You can interact with it by asking for explanations or requesting step-by-step debugging advice. This helps you navigate tricky problems more efficiently. In this video, we discussed how to use Microsoft Copilot to debug C# code. Microsoft Copilot is more than just a coding assistant, it's a powerful ally in your development process. It helps you catch errors early, suggest intelligent fixes, and guide you through debugging, making your coding process smoother and more efficient. In the competitive field of software development, writing clean, efficient code helps you better collaborate and maintain your code base. However, optimizing your code for performance and readability can be time-consuming. This is where Microsoft Copilot comes in. It acts as a virtual assistant, helping you refine your C# code in real time. In this video, we'll explain how to use Microsoft Copilot to optimize C# code. Microsoft Copilot is an AI-driven assistant that helps developers by providing code suggestions directly in a code editor like Visual Studio Code. Whether you need to refactor, optimize, or simply make your code more readable, Copilot can assist you at every step. Let's start by discussing how Microsoft Copilot can help you improve your code by rearranging and simplifying it. This is also called refactoring. For example, you might want to break a large, complex method into smaller, more focused ones. To illustrate this, imagine a method called process order in your order processing system, which handles everything from validating orders to sending confirmations, all in one block of code. This can quickly become cluttered and difficult to manage. You can prompt Microsoft Copilot by asking it to refactor the method to improve readability and maintainability. Microsoft Copilot suggests breaking down the method into smaller, more focused methods. To do this, you can divide the original process order method so that validating the customer's address, choosing the delivery company, and calculate shipping are handled in a separate method called process shipping. This restructuring makes the code easier to read, maintain, and test. Refactoring is crucial for making code more maintainable, but that's just one piece of the puzzle. Well-written code also should run efficiently. Now that we've explored how Microsoft Copilot can help with refactoring, let's investigate how it can optimize the performance of your C# code. Imagine you have a for each loop that processes items in a collection and checks if each item is valid before processing it. This loop could slow down your application, especially if the collection is large. You can ask Microsoft Copilot to optimize the loop for better performance. Copilot might suggest using parallel processing. By using the parallel.forEach function, the loop is rewritten to run multiple iterations at the same time. This change can significantly reduce the execution time, making your code more efficient when handling large data sets. Optimizing code performance can make your app perform better, but even the most efficient code can be challenging to work with if it's not easy to read. Let's explore how you can use Microsoft Copilot to enhance the readability of your code. Suppose you're working with variables that have unclear or ambiguous names. For example, you might have a variable named x that stores the total number of items from a function called getTotal. The name x doesn't give much context, making the code hard to understand. To make your code easier to understand, you can prompt Microsoft Copilot to suggest better variable names for clarity. The tool might assist renaming X to something more descriptive like total items. This small change can greatly enhance the readability of your code, making it easier for others to understand. You've learned how Microsoft Copilot can assist you in refactoring, optimizing, and improving the readability of your code. To get the most out of these features, it's important to know how to craft your prompts effectively. Let's review some best practices for doing just that. When using Microsoft Copilot, the quality of the suggestions often depends on how clear and specific your prompts are. Here are some best practices. First, be specific. Rather than asking for general help, describe the exact problem or the kind of optimization you need. For example, asking Microsoft Copilot to suggest a way to optimize this loop for performance will give you more targeted advice than simply saying, "Help me improve this code." Second, provide context. If your code has dependencies or relies on certain conditions, include this information in your prompt. This helps Microsoft Copilot understand the broader scope of your code. Finally, don't be afraid to refine your prompt or ask for additional suggestions. You can have a conversation with Microsoft Copilot. If something is unclear or you need more information, request it from the tool, and it will converse with you until you get the answer you need. In this video, we explained how to use Microsoft Copilot to optimize C# code. By effectively leveraging Microsoft Copilot, you can enhance your C# code's readability, performance, and maintainability. Remember to be specific in your prompts and to provide context for the best results. Imagine facing a challenging coding problem that seems overwhelming at first glance. The pressure is on and you need to come up with an efficient solution quickly. This is where the power of AI can be your greatest ally. Imagine having a tool that not only assists you in writing code, but also helps you overcome the most daunting coding challenges with ease and precision. In this video, we will explain how to approach and solve coding challenges using Microsoft Copilot. Software developers face several challenges when writing code. One is designing efficient and optimized algorithms. Another is writing code that processes large data sets. Finally, it can be difficult to write application logic that functions properly in all situations. Let's explore each of these challenges, starting with designing algorithms. First, algorithm design challenges are often tricky because they require deep understanding and critical thinking about how to write them for efficiency and optimization. Developers must consider complexities such as the time it takes to build an algorithm and the amount of code they must write to make it work. Writing efficiently can be difficult under time constraints. Microsoft Copilot saves you time because it can generate well-optimized algorithms quickly. This enables you to focus on refining the solution instead of starting from scratch. Now let's examine an example of how you can use Microsoft Copilot to help you with algorithm design. To tackle an algorithm design challenge using Microsoft Copilot, start by clearly defining the problem. Next, guide Microsoft Copilot with a specific prompt such as create an algorithm in C# that sorts an array of integers using the merge sort technique. Microsoft Copilot returns a C# implementation of a merge sort algorithm detailing each step of the process, from splitting the array to merging the sorted subarrays. By using Microsoft Copilot to help you design your algorithm, you can focus on the refinement of the algorithm efficiently while letting Copilot handle the initial implementation. Next, let's turn to one of the core tasks in programming, which is properly handling data. Let's explore how Microsoft Copilot can assist you with data processing challenges. When you're faced with a data processing challenge, Microsoft Copilot can assist by generating code that handles complex data manipulations. For example, suppose you need to write an algorithm that processes financial data by category. You can prompt the assistant with, write a C# function that takes a list of transactions and returns the total amount spent in each category. Microsoft Copilot generates a function that iterates through the list, categorizes each transaction, and sums up the amount for each category. By structuring your prompt effectively, Copilot turns complex data processing into a straightforward task. Finally, a third area that can be challenging for developers is managing how their code flows and works as a unified whole. This challenge focuses on the application's logic. Application logic challenges are difficult because they involve implementing the core functionality of your software, which processes inputs, makes decisions, and produces outputs. You need to map out how these components interact, which requires careful planning. Microsoft Copilot can provide a strong foundation by generating initial code. This helps you to build on this foundation and concentrate on enhancing the application's functionality. Let's break down how to use Microsoft Copilot to help you organize your code's logic. Microsoft Copilot can guide you through the necessary steps involved in structuring your code's logic. For example, you might say, implement a simple login system in C# that checks user credentials and allows access if they are correct. Microsoft Copilot returns a C# snippet that includes a method to validate user credentials and logic to manage successful or failed login attempts. Using Microsoft Copilot for tasks like this one helps you build the core logic of your application while you focus on making your application meet your design goals and delight your users. In this video, we explored how Microsoft Copilot can be a powerful tool for solving coding challenges. By using the right prompts, you can leverage its capabilities to efficiently manage algorithm design, data processing, and application logic. Practice with different prompts and you'll discover that Copilot can help you navigate even the most daunting coding tasks with confidence. Congratulations on completing the Introduction to Programming with C# course. Throughout this journey, you've mastered foundational skills in .NET development, explored essential programming concepts, and built a solid understanding of object-oriented and asynchronous programming. We began by laying the groundwork for .NET development, showing how Visual Studio Code fits seamlessly into your workflow. You learned how to set up your development environment, arrange project files, and understand the structure of a .NET project. Next, we expanded on this foundation by applying essential programming concepts including variables, data types, and debugging techniques. You practiced writing basic C# programs and developed a small project to consolidate your learning. After that, we moved into object-oriented programming in C#, where you learned to create and use objects, classes, inheritance, and polymorphism. We also explored various design patterns to develop your programming skills further. Then we explored asynchronous programming, focusing on key concepts like async and await. You discovered how to develop responsive applications that perform background tasks smoothly and efficiently. Finally, we explored how to use Microsoft Copilot to elevate your coding and debugging experience in C#. You discovered how to use this tool to boost code quality, simplify workflow, and easily tackle complex programming problems. You can now create dynamic applications, write efficient code, and leverage tools like Microsoft Copilot to enhance your development process. As you continue your journey in programming, remember that these foundational skills are just the beginning. The tech world evolves rapidly, so stay curious, keep experimenting, and never stop learning. Use what you've gained here to build, innovate, and confidently tackle new challenges.